Welcome everybody in Delta Lake tutorial / course because it's really deep. My name is Emil Kamiński and let's start this video by talking for whom it really is. So first of all, if you are preparing yourself for any kind of data engineering certificate in Databricks, there will be a lot of questions about the Delta Lake, and in this video there will be a lot of answers. Or maybe you are preparing yourself for the interview, it's worth to refresh the knowledge or even extend it, or you are simply trying to figure out what this Delta Lake is, how it works and how to use it. That's not the only video I can recommend. There is a video called Introduction to the Spark Architecture on my YouTube channel. It's really good, make sure you check it out. And the plan of the game is following. We are going to have three main sections. The first one is Introduction to the Delta Lake, where we will have a bit of theory, and then we are going to open a Databricks to see how can we create a first Delta Lake table, and we are going also to check out a couple of methods how we can ingest a data into that table. But here we will not go into the details. This is just a kind of a warm-up. Into details we will starting with the section number 2, where we will go through all the main features of the Delta Lake, and in each of that chapter again a bit of theory, and then we are opening a Databricks as soon as possible. The longest chapter here, I need to warn you, is a chapter demo, because this knowledge there is so fundamental that there was no point to split it into smaller pieces. And then the third section is the advanced optimization, where we will deep dive into partitioning, z-order, Bloom filters, or liquid clustering, and at the end a small recap. During this whole video we are also going to have a quiz which will help you to memorize all those things, and we are also going to talk about the secrets which nobody in the Databricks wants you to know. Let's get started. Let's go quickly through the part which I personally believe that it's less exciting but still very important, meaning a theory. So why do we talk about the Delta Lake? Well, some time ago we were all talking about the relational databases like Oracle, and everyone was happy. It was fast, easy to use, ACID compliant, it supported mainly a structured data, yes, but the structured data was the main thing we had. And then the world became more complex, we started to have more data and new challenges, and it was a big time for platforms like Hadoop, Apache Spark, or even for Parquet files, which were solving many of those problems, but they were again bringing on the table new challenges, like they didn't support ACID in such a way as the relational databases did, or they were not so easy to use. And this is where a Delta Lake came to the play, bridging that gap, and this is a definition which I think it's worth to read at least once, as they are asking about it on the interviews or on the exams. So Delta Lake is optimized storage layer, period. It's a default data format in the Databricks, yes, but you don't need to use a Databricks to use Delta Lake. You can use a Delta Lake outside, and we will be using a Databricks just for our convenience. And moving forward, very important, Delta Lake is open source software that basically extends Parquet with additional functionalities, which will be mainly presented in the form of really clever log, and the log will be kept in the JSON. We'll be exploring that in a second. And in the nutshell, it helps us to achieve that ACID compliance. You don't need to memorize it, we will be exploring that. Plus it delivers a set of really cool features, which again we'll be exploring and learning in this video. And to be more pragmatic, whenever we are talking about the Delta Lake, we'll be talking about two things: the file storage and the metastore. The file storage is super important because, as most of you already know, whenever we are reading or saving a data to the table, in fact, those data are being kept in the Parquet files on the storage. That's why it's so cheap to scale it. And what Delta Lake brings on the top of that, it delivers one of the things, it brings this Delta log. You will see a subfolder. In the subfolder, we are going to see a couple of different types of the files. But the main one, the most important, will be files ending with the JSON. That will be the main log, and it's really clever, you need to say it, it's really smart, and with it we will be capable to do really amazing things on the Delta Lake. And when it's going about the metastore, it's really a secondary. It's a place where we are going to register our tables to be able to run SQL queries on top of it, and there is a couple of options for the metastore. The most important is a Hive Metastore and Unity Catalog. Unity Catalog is what Databricks is promoting the most. Hive Metastore, this was default Metastore for many years. For the purpose of that video, we have decided to use a Hive Metastore because it's the easiest to understand how Delta Lake really works. It doesn't really matter which Metastore you use, the Delta Lake functionalities are the same. And that's it. And it's a time to create our first Delta Lake table. And we know that we are going to go to the Databricks because we have this picture of amazing lake called Lake Superior, which is the largest freshwater lake in the world by surface area, of course in America. And of course in this notebook, we are going to explore a couple of basic utilities which we need to know whenever dealing with the Delta Lake, as well as we are going to see a couple of ways how we can ingest a data into our table. Okay, we are in our first notebook, and in total we can see that we are going to have 14 notebooks to talk about Delta Lake architecture and to learn how everything in Delta Lakes works. When it's going about this notebook, this is very simple warm-up, but if you are preparing yourself for the Databricks exams or for the interview, this should already give you a couple of points. We will be using very simple cluster with the worker and the driver on the same node. If this is something new for you, I highly encourage you to watch a video about introduction to the Spark architecture. It's really good. And the plan of the game for that notebook is following. So those are really a basic things. So let's get started. All the data we'll be reading or writing to will need to be stored in something what is called the database, and it's typical for all the databases, not only for the Databricks. I can see a list of the databases available for me by using a command show databases, and that's what I'm going to get. The default database exists in all workspaces, so you have it as well. And here is some additional database which I don't even remember what's inside, created a long time ago. I can see a table in that database by switching to that database using use and the name of the database, like over here, and then running a command show tables. So Control Enter. As we can see, I have 4 tables over there. If I forget what is my working database, I can always verify it by running select and the function current database. This will give you the information about which database or which schema I am currently using. That's the name of it. And now I can create my own database or schema, because a database and schema in Databricks usually means the same. And the new created schema is called database. And now I can show all the databases just to verify that the schema has been created. It's over here. I can drop it by running drop database and then the name of my schema. Or instead of the database, I can use a word schema, create schema, and repeat the exercise. The outcome will be exactly the same. Now, once I have created my schema, I can create a table inside that schema by using create or replace table, the name of the schema, dot, and the name of the table I want to create, and then it's just a list of the columns of the table. Very simple. And I can query a data in the table. Just at this stage, of course, it's empty. Now, let's say that I would like to drop my schema because I decide that it's useless. I'm going to get an error, and the error is there because the schema is not empty. If I want to remove the schema which is not empty, I need to add the word cascade, which is another frequent questions on the Databricks exams. So drop schema, name of the schema, and cascade, and now everything is fine. And I can switch and use a default, which we'll be using for most of our notebooks, just to avoid the switching between the databases. Okay. So let's get started with creating empty table for that notebook. So at the beginning, I make sure that that table does not exist because I was running notebook for a couple of times and I don't keep a track anymore if the table exists or not. I want to start with drop table if it exists, the name of the table, and then I'm creating the table with 2 columns, integer and string. Very simple and similar to what was above. And then I can again query of the content of the table, which at this stage is of course empty. Now let's look on the first method of ingesting data into the table. We can use a statement insert into the name of the table and the values. This is the basic way of ingesting the data, and what it does, it takes the current content of the table and add on the top of it those 3 rows. Now once I will query the table, I will have exactly those 3 rows inside. I can add additional 2, and in total I'm going to see 5 of them. And that was insert into. The next thing we want to check is insert override. The syntax is the same, the name of the table and the values. The big difference between insert into and insert override is that insert override will basically ignore any existing data in the table, and once I will insert override one row, I'm going to see there exactly one row, like over here. If I would create insert override, the name of the table, values, and 3 rows, how many rows I will have in total? Of course, I'm going to have 3 rows because the previous one has been ignored. So we can say that insert override is similar in a way to delete and recreating the table, but it's faster because it doesn't perform the delete operations under the hood, as we are going to see later on. Now, moving forward, in the Databricks or in the Delta Lake, we have a set of very useful utilities which allows us to obtain some information about the tables. And the basic utility is called describe. We can invoke it by writing the full describe or just the beginning, like here, this and the name of the table, and we are going to see the list of the columns in our table, like over here. We can also write the full describe and the outcome will be precisely the same, no different. The another utility, it's a bit different, describe formatted and the name of the table. This time, besides of the list of the columns, we are going to get additional information, which we can see over here. Like at the beginning we have a list of the columns, but moving forward, the row number 10, we have information about in which databases the table has been created. Moving forward, we have information about the location of the files for that table. We will be querying that location shortly. And the information, oh, it's over here, type managed. This will be investigating shortly as well. And let's move on. Very similar utility to describe formatted is describe extended, which at this stage will give us exactly one-to-one the same results as the formatted. Once we will have a data in the table, there will be a slight difference. With describe extended, we will get one additional row with the information what's the size of the statistics for that table. But at this stage, describe extended gave us one-to-one results to describe formatted. Very useful utility. And a bit different is describe detail. This time we are going to get only one row, like over here, with the information about the format of the data, so we saw it before, the name of the full name of the table, like default dot the name of the table, location of the files, created, last modified. So similar information we are going to see here. If we have some partitions or clusters for that table, we will be creating them in the future notebooks, but we are also going to see a number of that files for that tables, the size of those files, and some additional parameters like properties. Deletion vectors is enabled, we'll be explaining that shortly, and some statistics. And moving forward, as we know the location of the files for that table, which is over here, it was also given once we run the utility describe extended over here, we can query that location to see what's there. And that's one of the reasons why we have decided to use the Hive metastore instead of Unity catalog. In the Unity catalog, this location may be protected and you will not be able to query this location so easily as I'm doing over here. You will need to go through Azure portal or AWS portal to see the files. I can query that straight from the notebook. And what I see here is I have a files ending with Parquet. Those are files with the data. And I also get a subfolder which is called a delta log. We'll be exploring both in the details shortly. The last utility which I wanted to show you in this notebook is called describe a history, which will tell us what happened with the table and who did it. So we can see that the first entry, version 0, was the operations create a table and some parameters. So some parameters for that operations, which are over here. The further operations to the tables was the operations with adding a data, and I will have here some information about first of all operation, but if I will scroll to the right, I will have here information about some statistics. So like in our case, with this operation, one file has been added with one row, and that's the size. Okay, let's move on. Another very important thing to talk in this warm-up notebook is something what is called CTAS, and this is super frequent questions on Databricks exams for some reason. CTAS stands for Create Table As, and to demonstrate how it works, let's look on this dataset. This is a sample dataset available in the all Databricks notebooks. If you are not using a Databricks, don't worry, you can use any other file. We are using a Databricks for our convenience, but of course you can use a Delta Lake outside of the Databricks as well. And in this location, we have one CSV file over here. And now we can easily query the content of that file using the select star from CSV. And that's how our file looks like. But we can also very quickly and very easily transform that file into the table by using exactly CTAS, create or replace table and the name of the table as, and the rest is the same. So let's fire this command. And let's use the utility which we know and like, describe extended, to see the name of the columns. Of course, those names are wrong because we haven't specified the schema for the table, but scrolling down, we see first of all the location of the table, and location is important. They are asking on the exams what is the default location of the files for the tables registered in the Hive meta. So that's the location, user Hive warehouse, and then the folder is the name of the table without any extension .db or anything like that, just the name of the table. And we also have here information that this table is type what is called managed. So as we are going to see in a second, we have two types of the tables here in the Databricks. We have managed and external, sometimes they called unmanaged. So this one is managed. And what it means is that we can query that location managed by Hive Metastore, and we are going to see a files for that table. Again, a Parquet files and data log. So a schema of that folder is precisely the same as for the table we have created before. And now what is important is that once I will decide to drop that table, it's not only metadata that are being removed from the Hive Metastore, but also all those underlying files, which we can see over here, will be removed as well, which we can verify by querying that location and getting an error that this location does not anymore exist. Alternatively, we can use a CTAS with one additional keyword, very important, which is location. So at the beginning, create or replace table, name of the table, then the keyword location, and the rest is the same as select star and from CSV. By adding the word location, this is the information for the Hive Metastore or Unity catalog, depends on what you use, that we don't want to create a managed table, we want to create what is called external table, meaning we don't want the Metastore to manage underlying file. And let me fire that command and show you what it means. So the table is being created, and then I'm going to fire the utility describe extended. Scrolling down, I'm going to see the information that the type of the table is external, and the location of the files it's following. It's exactly what I have specified after the location keyword over here. So this is different location. This is not a location where the Hive Metastore is saving a data by the default. I can still query that location and I'm going to get exactly precisely the same outcome, just the location is different. So Parquet files and delta log. But if I will decide to drop that table, drop table and name of it, I'm going to see that the files in that location remains untouched because Hive Metastore, neither Unity catalog, are not entitled to remove it. They are not managing this table. This is external table for them. So whenever you are going to see a location keyword on the exam, it's going to be external or unmanaged table. And now the last thing for that notebook. Let me introduce you to additional method of ingesting data to the Databricks table, which is very clever, and it's called copy into. For the purpose of a demonstration, I will use another dataset prepared by the Databricks, so again, available in all workspaces, which again with the flight data, which are over here in the CSV file, one file per year, starting with 87, couple of files, and let's say that I'm expecting to get those files into my folder, which I wanna monitor, and depends what arrives, I wanna ingest that into the table. First of all, let's just see how the files looks like, so you get a feel of it. That's our file. And the first thing is that I'm creating the empty table with the appropriate schema. So create table and the name of the table and couple of columns, Control Enter. And I'm going to create a folder where I will be expecting those files using dbutils fs mkdirs. folder has been created, and now I want to copy one, not everything, one file from that data set into my folder, only one file. So again, using dbutils fs-cp, file has been copied, and now let us use a copy into the name of the table from the location where I have right now one CSV file with the information that file format is the CSV, and with additional format options saying that header equals to true, because in those files there is a header, so the first row should be translated into the column names. And once I will run it, you will see why this is clever. Once I will run it, I will have information that there is around 5 million rows ingested from that location into that table. I can verify that statement by running simple select count from that table and getting exactly the same number. What will happen if I will run copy into one more time? So we don't change anything, the same data in that folder, running the copy into one more time, and we see the information that number of the inserted rows is 0, because copy into recognizes that all the files in that folder has been already ingested. So no matter how many times I will run it, it will not ingest again the data which has been already ingested. What I can verify by copying additional file to that folder, and let me go over here, and now I will switch a year, change a year 88 to 89, copy another CSV to my location, and run a copy into again. And this time it will recognize that there is a new file which has been arrived and will ingest only this new file. And again, around 5 million rows has been ingested according to the copy into, which we can verify by running select count. We should have around 10 million rows in our table, and that's what we get. And of course, if we will run a copy into without copying additional data, it will recognize that all the data has been already ingested, the number of inserted rows 0, and the number of the rows in our table doesn't change. So very clever, simple, useful utility, copy into. That's it for that notebook. Key points to remember. CTAS stands for create table as, very useful. Insert into append a data to the table, and insert overwrite ignores whatever there is in the table. But insert overwrite don't remove a files on the storage. That's important, because in a couple of notebooks we will learn about the functionality which is called time travel, and with that functionality we will be able, even after doing the insert overwrite, restore a version of the table from before we run that command. We saw the utility which is called copy into, which keep a track record of what has been ingested and ingest only the new data, super useful. We saw a default location for Hive managed tables. Well, this one is important because they are asking about it on the Databricks data engineering exam. And we saw the difference between the managed and the external table. If we drop the managed table, we drop both metadata as well as data. With the external table, we drop only the metadata. What is interesting is that you can actually register the whole schema as external using the keyword location, and you can do that as the experiment. You can create there some tables and check what will happen if you drop that schema. And here is the summary of the main commands we have used in that notebook. And it's time for a demo. And that's actually going to be the longest notebook in our video, because it's the most fundamental. It's super important to understand everything what's happening over there. And here we have a Lake Victoria, Africa's largest lake by area, the world's largest tropical lake, Tanzania, Uganda, Kenya. Alright, we are in the notebook number 2, the demo of Delta Lake. And the purpose of this notebook is, well, first of all, learn about the basic behavior of the Delta Lake, meaning what will happen if we will insert some rows, update, delete, or merge into our table. Second thing is to understand a Delta log structure and meaning. We saw it in a previous notebook on the very high level that there is some subfolder. In this notebook, we are going to deep dive into it. And the third thing is we are going to start understand the importance of the file skipping, which is a huge thing in Delta Lake and Databricks. A lot of optimizations mechanisms are about avoiding reading unnecessary files. And about the unnecessary files, we understand the files which for sure doesn't have the data we are looking for. So let's get started. And the first things first, as the small setup, we are going to turn off some of the optimizations mechanism of Delta Lake. Not that they are bad, even opposite, they are great, as we are going to see it in a couple of notebooks, but when we are learning, we want to keep things simple and we want to avoid things happening automatically. This way, it's easier to understand how the Delta Lake works under the hood. Now once this is done, we can go and create our table, which we'll be using for that notebook. Table it's called demo and it's having 3 columns, ID, valid and a name. Just shortly after we created the table, we reminded ourselves that we need to set up some limitations for it. The first limitation, we want to avoid column valid to be null. Therefore, we are writing alter table demo, alter column valid, which is the name of the column, set not to null. And the second limitation, we want to add a small constraint. We want to control our ID. And we write alter table demo, add constraint. Here is the name of the constraint. It's not the name of the column, it's the name of the constraint. And a check. ID larger than 0 and less than 1 million. So Control Enter. And now we can use the utilities, which we know very well. Describe a demo, which will show us the list of the column, and describe extended demo, where we are going to get a bit more details. Also, if we scroll to the bottom, we have a table properties, which will also include the constraint, which we just added to the table. Okay, let's look what's inside. Once we run describe a detail, we have a path to the folder where all the data for the table are located. In the Databricks Delta Lake, whenever we are adding a data to the table, those are being saved in the form of the files. So let's query that location. And what is not any surprise, we don't have any parquet data here because we haven't inserted anything to our empty table. Nevertheless, we have a Delta log folder, so we can query this one. And what is surprising is the number of the files which are located in that folder. Even though we haven't added any data to the table, we have already 6 files over there, 3 CRC files and 3 JSONs. JSONs are the most important. CRC is more about the internals, how the Delta Lake works, but the JSON, this is really the main functionality of the Delta Lake. Once we will look into our first JSON and the number starts with 0, and we enter the focus mode, so it's easier to read. What we are going to see is, well, first of all, we are going to see a different columns, and the column will be different, depends on the type of the operation we will be performing on the table. In our case, the first column is called commit info. The JSON file is being generated whenever there is a commit happening, and commit is done by the operations which modify something in the table. It can be creating the table, adding columns, changing data, adding data, and so on. In our case, this commit was create table. So this was our first query which we have run to create that table, and here we have the information created table, plus we have some information about the properties, timestamp, and so on. If we will scroll to the right, we see a second column which is called metadata, super important, where, once we will extend it, we are going to see a schema definition, so type struct field. So in our cases, we have 3 columns. We have ID, valid, and name, and for the ID we have information that the type is integer and it's nullable. For valid, the type is boolean. And the type, and again, it's nullable. Why it's nullable if we have just added the constraint? And then we have a third column, name, and the type is string, nullable as well. So that was a first JSON file. If we go and look on the second JSON file, named 1, we are going to see that the columns inside the JSON are exactly the same 3 columns. Let's look into the commit, but this time there was a different operation creating a commit. It was operation change column. And here we have the details that valid, boolean, and it has set up the nullable to false. And then once we will go to the metadata, we can again find a schema for that table. Just this time, once we will find our column valid, it's nullable, it's false. So we have changed a type of our column, it's not longer nullable. And once we will look on the third JSON, so I'm just changing here a number to 2 and executing this command once again, scrolling to the left, the structure of this JSON is again the same. We have a commit info. This time the operation was add a constraint and the information about the constraint, and the metadata, which we can look into the details as well, but nothing's changed in the schema. Just in the configuration we have information about the constraint added. That's how the JSON looks like. So already the first information for us is that after every operation which adds a commit, we have a new JSON file describing that commit. Not all the operations are creating the commits, but for those who are creating the commits, we are going to have a JSON, no matter if we are writing any data to the table. Now, for the sake of ticking all the boxes, let's look on the second type of the file located in the same folder, which is ending with the CRC. So let me read that as a JSON as well and go to the focus mode. So this file is more for the internal purpose of the Delta Lake. This is a checksum of the corresponding JSON file. So for every JSON file, so for every commit, we are going to get a checksum like this file created, and this checksum will be checked whenever Databricks or other engine will be reading Delta log. It will go to the checksum to see if the Delta log has not been corrupted, for instance by the storage problem. So the primary purpose of this CRC files, which we are going to see in the folders, is a data integrity. Those does not bring any additional functionalities for us. Those are only to secure that Databricks can deliver on the ACID promise, which we will explain in a couple of minutes. So RCS files important, but we will not be diving into that too frequently as it's more for the Delta Lake internal purposes. And once we will describe the history of the demo, we are going to see those three informations, because every time we are using the utility like describe, formatted, extended, history or detail, those utilities are reading a data either from the Hive or Unity catalog metastore, either directly from the Delta log, which we just seen. So here we have the information about the three commits, and we have three JSONs. The first one was create a table, then change column, and then a constraint, and then some operations parameters, and so on. So it's not that always we will need to go to the Delta log. Frequently the information which we get through the utilities like describe histories will be enough for us to understand what's happening. Right now we will be going to the Delta logs to understand the details of the mechanisms. Okay, so for the time being the table is empty. Let us enter one more row using insert into table values 1 through Alice. And let's take a look on the data now. So we are querying the location where the data for the table is located. And right now we can see that there has been one snappy Parquet file created. This file contains the data which we have inserted into the table. Once we will look into the Delta log, we will see the fourth JSON, the JSON corresponding to the latest commit, and the latest commit was the insert to the table, and here it comes, it's number 3. Now let's create or let's insert another row, just this time the ID is -1. And if we remember, we set the constraint to ID to be anything between 1 and 1 million. So once we will try to perform this operation, we will get an error with the information that we are not following the constraints, right? I hope that right now you are sitting down. If not, please do, because once we will query the folder with the data, what we are going to see is the second Parquet file with the data which shouldn't be inserted to the table. So what happened? Let's take a look on the Delta log. So I'm querying the same location, just a Delta log. And right now I see that while the Parquet with the data has been created, there is no additional Delta log for it. The last Delta log which is there is a Delta log number 3, the fourth commit, which we queried before. And if we look inside, that's the commit for the operation, which was inserting, I will unzip it, which was inserting one row where the ID was named, the name was Alice. So there is no Delta log for the -1 ID. There is only a Delta log for the operations which have been successfully completed. Okay, let me exit the focus mode. And if we describe the history of the demo, the last operation which has been recorded was the write, which was successful. There is no entry for the unsuccessful operation with the ID -1. And we can query just to see how the last CRC file looks like. Although it's not going to for us anything interesting, is just a checksum for this JSON file. Moving forward, let's insert multiple rows in our table. And now the question to you: how many Parquet files and how many Delta logs JSONs will be created after this will be completed? And of course, the answer is one Parquet file and one delta log. Let's take a look. So if we query the Parquet files, so we see now 3 Snappy Parquet, and Snappy is just the compression format developed by Google long time ago for the Parquet. And if we drill down into the delta log, we will see one more additional commit, which is commit number 4. It's over here, and we can read it in the same way as we were reading all others, but we will pay attention to something else now. As we can see, the columns in our JSON has been changed. Right now we don't start with the commit info column, but we start with the column which is called add. The commit info is later on, but the first one is add. Once we will look into it, we will see that there has been one file added, Snappy Parquet. And over here, we are going to get something what is super important. We are going to get a statistics for that file. And we have the information that number of the records is 3 in that file, as well as we are going to see a mean value, max value, and the number of nulls. So mean value, in our case, ID 2 name Bob, max value, ID 4 max Steve. And this is super important. The Databricks by default is collecting the statistics for the first 32 columns. In our case, we don't have 32 columns, we have less, even though not all the columns are included here. We are missing a column valid. The case is that the Databricks or the data lake does not collect statistics for all types of the columns, and in case of the column valid, which is type Boolean, Delta Lake believes that collecting statistics for it is just simply unusable, so it's primarily focusing on collecting the statistics for the data types like the integers or numbering or strings, like in our case. And why this is important? This will help us to skip some files while reading. By having these statistics, like over here, the Databricks will know that, for instance, if we are looking for the IT number 0, there is no point to read that Parquet file. It simply doesn't have this data. This data is for the ID between 2 and ID between 4. Okay, and moving to the right, we have the commit info. So as we have already seen in the past, commit operations is write, creating the commit, and that's it. Let's exit the focus mode. And let's now do a bit different operations, which is updating the value. So looking on our table before updating anything, those are the records which are inside, 4 records. And what we want to do, we want to change the name of Alice to Alice updated. I'm sure that Alice will be happy because of that change. And if we look on the table, into the table one more time, just to verify that action was successful. You cannot trust everything what's in the screen, especially that in the era of the fake news. We actually see that this time it was true. The Alice, the name has been updated to Alice updated. It's very creative. And looking into the data, what we are going to see that actually there was additional Parquet file created, which is a very interesting approach to updating the data. Because of course, the natural behavior would be to grab a Parquet where we have a data about Alice and modify it and write it to the storage one more time. Not in case of the Delta Lake. Delta Lake believes that it's better to write a new value to the separate Parquet than to modify the existing, which is first of all faster. And the second thing, very important, we are going to see shortly the capability which is called a time travel. So by not modifying a data, but by just adding the new data, we will have in the future possibility to move back in time and to restore the previous version. Okay, let's take a look into the data log. So everything here is the same, just we are grabbing the latest commit, which is the commit number 5, Control Enter, and going directly into the focus mode to check what's there. So let's remember, we are doing update operations, but we have a column which is called add, because the Delta Lake is creating the new Parquet, which we have seen, with this type of the data described by those statistics. And going to the right, we can see that commit info is exactly update, that's correct. And going to the right, we see another column, which this time is called removed. And once we will scroll it down, we are going to see the information that this file should be avoided from reading moving forward. And this is the file which contained the original value for the Alice. So the moment we add Alice to the table, that's the file which has been created. Now we have modified just the new data we have written to the new Parquet file, and delta log is keeping the information that the old Parquet log can be removed in the future or can be kept by the Databricks or Spark or other processing engine. And here is another very important thing to remember, that delta log is frequently called a single source of truth. The reason being is that whenever we are reading a data with Spark, Databricks or whatever else, we don't go to the snappy Parquets directly. We first, or Spark first, go to the delta log to see which files are worth to read, which can be skipped and which has been removed. And talking about skipping files, let's take a look on the very sophisticated query, select star from demo, and the results are not surprising. We have 4 records, but what is interesting is how this has been executed. So we have 2 jobs, 78 and 79, and in the Databricks I can jump directly to the Spark UI. If you don't know how to use the Spark UI, highly encourage you to watch an introduction to Spark architecture, which got really good reviews. And now we will go to the SQL data frame, as we are using a data frame API, find a job 7879 over here, and of course scroll down. And what we are looking for is the number of the files which has been read by the query select star from demo. And we have it over here. Number of the files read, 2. So the Databricks has read from the storage 2 files to display all the data, all the records which we requested him to do. If we modify our query and we add the constraint select star from demo where Alice equals to Alice updated, what will happen now? How many files Databricks will read? Will it read 2 files, or it will use a delta log to identify the file which has Alice updated and will read only this file? So we can check it in the same way, finding job number 80 over here, scrolling down and finding the total number of the files which has been read. Number of the files, 1. So this is the beauty of the delta log. Apache Spark or the Databricks didn't jump directly into the Parquets. It jumped onto the data log, and data log told them that, hey, you know, the Alice updated, that's in this file. There is no point to read all the files, right? Let's close this one and let's change our constraint and let's look for a data where ID equals to 1. So tell me, how many files we will read now? Control Enter, and the answer is 0. There is no even job created. It was so simple for the Databricks to figure out that this data does not exist, that it didn't even spin off any job. Simple as that. And this is beauty of the file skipping. Data log by itself, it's powerful optimization mechanism, and many advanced optimizations mechanism in delta log Databricks will be about fine-tuning that mechanism, taking it to the next level with different clever algorithms and approaches to aggregating, segregating files on the storage. Okay, before we close this notebook, there are 2 more operations to check. The first one is very simple, deleting a row. So we have our table, just we realize that Alice updated is here by mistake. So we are deleting records corresponding to Alice updated and straight away going to check our Parquet files to very quickly understand that this time there was no new Parquet files created. Instead of that, we started to have something in our folder, what is called Deletion Vector, which we will explain in a couple of moments. But in case of the delete, there was no new Parquet files created. If we take a look on the latest JSON file, on the latest commit, and going to the focus mode, we see that commit info, it was of course delete, like over here, and once we go to the right, we see only column remove without any more column add. Only column remove, and once we will scroll it down, we have the information about this file being unnecessary for the Databricks to read moving forward. So let's exit this one. We can also check the history, but here no surprise are waiting for us. And we can go to the last operation in this notebook, which is merge. And merge is very important. Whenever you will be working as a data engineer, this is something what most likely you will be using frequently. And to explain a merge, let's prepare the stage first. So let's take a look on how our table looks like. Select star from the demo. And this is our existing table. We have 3 records, Bob, Steve, and Ray. And now let's say that we have a second table with the updates. Meaning maybe a new records, maybe modified records, or maybe the information that some of those 3 records should be removed from our demo table. And that's how our demo updates table looks like. It's having the record for Ray, just this time the column valid has been changed from false to true, so we should update the information for array. We have a new record Mickey, which was not existing in our original table, so we should take that record and add it to our table. And then we have the information about the Bob that this should be deleted because it's in our table by a mistake. And how to approach it? And the answer is using very clever operations, which is called merge. And sooner or later, once you will start using it, you will need to check in the documentation what's the precise syntax, because there is a fair amount of options, but on the high level, that's how it looks like. Merge into, and here we are giving our target table, so our target table is a demo, using a table with the updates, so in our case it's a demo updates, and now it's similar to join. On, and here we are giving a key, so demo ID equals to demo update ID, like here. And now we are stating, if you know a Python or any other programming language, this will be sort of if-else. If matched and this operation, so otherwise, if this record exists in the table, but the operations has been marked as delete, then delete. Else if, meaning if the key is matched, but no additional conditions, then it means that we should update the fields. Like in our case, it was about Ray. We are changing the value from false to true. And if any of those 2 conditions above are not met, so it's in like Python or other programming language, else if, when not matched, then, meaning all previous conditions were not met, insert, typical for SQL insert. So all those 3 operations, delete, update, insert, are typical. It's just this merge syntax, something new. Merge into using on, and when matched, when not matched. It's not really complicated. You need to get used to that a bit, but it's fairly simple. And then once we execute it and we look into our table, we will see that all the records have been updated as expected. We have a new record Mickey, Ray has been updated, and Bob has been removed from that table. And if we look into the history, we can see merge as a commit number 7. Actually, in our case, Databricks kicked off some automatic optimization. We can ignore it for time being. We can focus on the operation number 7 on the merge, and we can look on the commit information into the JSON files. And we will see that some files has been added, files with the data plus some deletion vector, which we'll discuss in a second. We also see that some files has been removed, so no surprise over here. That's how the merge looks like. Very useful. And the last thing to mention before we will close that notebook, that it's not always the data log will be kept in JSON. So far we were talking about the JSONs, but it's not always the case. The problem is that if we would create a new JSON file after each and every operation, with time we would start having the massive number of JSON files, and only operation to read all those JSON files by the Databricks on Apache Spark would take a lot of time. And to address that issue, we have something what is called checkpoint. And to demonstrate that, let me execute multiple insert operations on our table. And actually, after a couple of minutes, let me interrupt it because it takes really a lot of time. And the reason being is the way I wrote this for loop is to have every insert as a separate operation. So every insert is creating a new commit. And this is of course slow, but it's sufficient to demonstrate you one thing. Once we will go to the data log, we will see number of commits, over 100 for sure. We can scroll down, and once we will start scrolling down, we will see that not all the files are the same. From time to time we have a file which is called compacted JSON, which is like the intermediate file after some number of the JSON created by the data log to avoid going through all the JSONs all the time, otherwise it would be slow. And once we will scroll it down even further, we are going to see the files, which will be a parquet, like this case. Checkpoint, parquet. After some number of the files, Delta Lake consolidate all the information from the JSON Delta logs commits into the checkpoint parquet. And why this is important? First of all, it helps to read a data from the Delta log way faster. And the second reason, of course, reading the parquet is way faster for the Databricks than reading a JSON. Let me find the last checkpoint. It's over here. And let's take a look on how this looks like. And actually the query I have already prepared. So Control Enter, and going straight away into the focus mode, we will see here that this is nothing else than the information consolidated from all previous JSONs which we have seen, just maybe with the difference that some information like the statistics has been already parsed and are no longer read by the Databricks from this JSON, but are right now in the structured data type, so it's faster for the Databricks to read it. So it's really just the optimization mechanism of reading the Delta log way faster than it would read all the JSONs before. And before I close this notebook, the last thing to demonstrate. So here we were treating each and every insert as the separate operation. We can of course achieve the same by combining all of those inserts from that for loop into the one query and try to execute everything as one operations, which will be faster, but it's not what I'm trying to prove. I'm not after showing you the speed. I want to show you something what we will discuss in the second. So here I have some simple code, not so important, but just something handy to find me the last JSON in Delta log and the last parquet in our data format. And what I wanted to show to you is to performing exactly the same insert as we were doing in the loop before, just in this case to perform it as the one operation with a small caveat. At the end I'm adding -1 true error. So I'm adding a record which I know that it will not met a constraint on the table. If we remember, we have a constraint that ID needs to be greater than 0. So this record will create an error. The question here is, what will happen with the records which are following all the constraints, with all the good records? If we look on our query, that's how it looks like. At the beginning we have insert into demo values, and we see here a number of the correct values. ID is greater than 0, true, so there is no nulls, and we have some name. Just at the end we have our buggy, well, come on, we have our buggy record at the end over here, so that's a troublemaker. And if I execute this query using Spark SQL, I'm getting, of course, an error because we have our record with -1. But let me verify now what's the last parquet data and what's the last data log data. As we can see, the last JSON is still 114, but the parquet file has changed. So now it's F5. So Databricks or Data Lake started to add a data, but once the error has been hit, the operation was not completed, commit was not done, so whatever data has been written to the storage are not valid from our point of view, because as we remember, Spark Databricks treats a Delta log as the single source of truth, so anytime it's looking for the data, it will go first through the Delta log to figure out which files to read. And whenever we have such corrupted parquet file like this guy, it will simply be skipped. Okay, that's the end of the longest notebook about Delta Lake demo. And we are back to slides because I want to pay your attention to Deletion Vector. This is a relatively new feature in the Delta Lake, and you are going to see a ton of documentation referring to it, but the idea is simple. Whenever we are using operations such as delete or update and frequently merge, those operations will use a deletion vector to mark existing row as removed or changed. And with that functionality, we avoid frequent rewriting of the parquet files. And let's see it in the Databricks. So here we have another lake. It's called Loch Ness, home of the Loch Ness monster, also known Nessie, Scotland, UK. Nessie, if you are watching us, don't forget to subscribe. And we are now in the third notebook of our Delta Lake tutorial, this time about deletion vector, and this time it's going to be short. The reason for that notebook is because I see many people are confused how to read, how to interpret deletion vector from the delta log, and I totally understand it. It's a bit confusing. So let me hit run all button and let's analyze step by step what's happening over here. So at the beginning we have a small setup just like before, and then we are creating very simple demo table, again the same as in the previous notebook, where we are adding one row and immediately after that we are removing that one row. So once we will look into the folder behind the table, we are going to see one Parquet file, deletion vector and delta log. And checking delta log, we see 3 commits. Checking the latest commit, that's what we are going to get. At the beginning, in the first row, we have information about the commit itself, and then once we will scroll to the right, we see the second row for remove. And in the remove, we have information that this Parquet file can be removed, can be skipped, which is normal, intuitive. In that Parquet file, we have only one row, and we just remove that one row, so this file is not needed anymore. Okay, let me get back to the standard view, and let's compare it with a bit different situation, starting fresh, recreating the same table, but this time inserting 3 records, and straight after that removing one of it, and our selection is Bob. So Bob has been removed from the table, and if we look into the folder behind the table, we see exactly the same structure. One Parquet file, deletion vector and the delta log. So again, checking the last commit to the delta log, and here it is. Let me go into the focus mode. Now we see 3 rows in that log. The first row is the same, is the information about the commit. The second row, surprisingly, it's also the same, it's information about removing a file. But how could we remove the whole file if we have there 3 records and only one of it has been removed? And the answer is that straight away after this being removed, there is information in the delta log. Whoa, hold on a second. This file is still important, it's exactly the same file, 937, and here we are removing 937. So here is the information. No, this file is still important, just the way to read it, dear Databricks, is you can read the file, but please pay attention that there is now deletion vector assigned to that file, pointing out to one record which should be ignored. So what is very important when reading a delta log, it's not to read it only from left to right, but row after row. The removal was a second row on the right, but the last step in that log is to add back this file with the information about the deletion vector. The delta log itself keeps a track of changes on the file level. There is no, in the delta log, there is no mechanism to track row level changes, and the deletion vector is one of the mechanisms in the delta log allowing us to track row level changes. Okay, that's it for that notebook. And after doing a demo, it's important to say that Delta Lake is not the only such project. There are others. 2 the most important, which are also open source, is Apache Hudi and Apache Iceberg, which you can explore by yourself on those web pages. And the key points to remember. Well, the basic operations, which we have seen a minute ago, like insert, update or delete, doesn't modify the Parquet files by themselves. There are other operations which we are going to learn which does it, but those does not touch Parquet data files. Instead of that, we have a wonderful delta log which keeps a track record of what is valid and what's not, and we have also a deletion vector which work on the row level. And delta log, sometimes it's called a single source of truth because Apache Spark doesn't go directly to the Parquet data, but it first goes to the delta log to figure out which Parquet files it's worth to analyze. And delta log, the JSON files, keeps a statistics for the first 32 columns to support file skipping. Unless some columns are nested, then this number goes down to consider the nested columns. And this is important because whenever we are designing a wide table, we should think which column to put at the beginning. And also they are asking about it on the Databricks data engineering exams. And if you are using the Unity catalog may not let you to see a delta log for the managed table. You may need to go through the Azure portal. And this is a summary of the commands which we have used in that notebook. One thing which we need to discuss is what ACID means and how Delta Lake support it, but we are going to do that very quickly. I have a couple of slides prepared. I will not read them. You can pause the video and read it by yourself. Instead of that, I will use a very simple explanation of what each letter means. And A stands for atomicity, which means all or nothing, and we have already seen it in the previous notebook. The last step for each and every transaction is to create a commit. And the commit is created only if the whole transaction is successful. For instance, if we are trying to insert multiple rows and we failed somewhere on the way, the commit will not be created. Therefore, even if the Parquet file has been created, it will be ignored because there is no commit. Very simple, all or nothing. The second letter is also very simple. C stands for consistency, and it means that transaction only makes changes to the tables in a predefined, predictable way. Using a simple words, there shouldn't be a way to mess up the table. And in the Delta Lake, the first mechanism which secures it is schema enforcement. We have seen in the JSON file a schema definition for the table, and the Delta Lake will make sure that whatever we are trying to write to the table follows that schema. Unless we are very explicit in saying to the Databricks, you know what, actually I wanna override that schema. But it's still in a very controllable way, and we are going to see it in the next notebook. Simple. Next one is isolation, and this is super cool. So basically it's about having the concurrent transactions don't interfere with or affect one another, so you can have multiple processes working on the data at the same time. And here is very interesting term which is called optimistic concurrency control. Originally in the databases, when you had a process which started to work on one table, the database would lock that table and another process cannot touch that table as long as the first process is operating on it. Delta Lake is taking different assumption. It basically assumes that the data anyway is so huge that those processes are most likely working on the different part of the data, so it allows them to continue and it verifies if there is a collision during a commit. So, to demonstrate it, let's assume that we have a table, and in that table we have already one commit, log0.json. And now we have two processes starting to work on the data in exactly the same time. Both of them record what is the last commit in the data. So commit number 0. It happens that process number 1 is faster, so it writes a commit number 1, log1.json. Then process 2 is finishing its job. It also trying to write log1.json, but it's already taken. So what does it do? It doesn't throw an error into the user face straight away. It checks if that commit number 1 has modified a data on which process 2 was working. If not, everything is good. It just creates additional commit number 2. It may happen that there is a collision. It may happen that, for instance, process number 2 is trying to delete a data which has been already deleted by the process number 1. Then we are going to get an error. Otherwise, everything is silently happening in the background. So that's the isolation. And durability is probably the simplest. Whenever we have a transaction which is successful, it's about guaranteeing that those results will not be lost. And in the Delta Lake world, this is a bit abstract, but in many databases, the data and the results of the transactions are first being stored in the memory, in RAM. So then when you have, for instance, a power outage, you can lose your results. In Delta Lake, everything is straight away being written to the storage, including commits files, and the storage is being considered as durable. And that's a D, durability, simple. Okay, it's time to learn about schema enforcement and evolution. So in previous section, we said that we have two main features to secure C in ACID. First one is schema enforcement, very important, write-time validation, and basically the role of that is to figure out if we are not trying to add additional columns or the data types which are not according to the schema. And then we have also a schema evolutions, something what will allows us to modify a schema once we write a bit. We don't have a full flexibility, but we will be able to do a couple of things, as we are going to see, like add additional columns. And to enable a schema evolution, we have two ways of doing that. The first one is in Python. We need to use option merge schema equals to true. And the second one is by enabling the global variable auto merge enable true. And I need to warn you, I see many people super excited with the fact that they can do a schema evolution, but I don't see too many cases where this is a good idea, because once you enable the schema evolution, you can destroy downstream systems which are using the data by changing the schema, by adding additional columns, and basically you are losing a bit of control of the data which is flowing through your system. But anyway, let's see it. And here we have the deepest and the coldest, the oldest lake in the world, in Russia. And we are now in the fourth notebook about schema enforcement and evolution in the Delta Lake. So at the beginning, let's do some preparation. We create a demo table with 3 columns and inserting a record, which is very good record because it's having 3 columns as per the type definition. So right now in the table there is 1 entry. But we are talking here about the schema enforcement. So let's check if it really works. As we all know, seeing is believing. We cannot trust everything what we read in the Databricks documentation, right? So let's try to insert a record with 4 columns. So first 3 are the same, and then we are adding the third one, and let's see what will happen. And we are getting an error, a schema mismatch detected. So that's good, that looks like a schema evolution really works. But what will happen if we will try to add a record with 3 columns, just one of it is changing the type. Initially it was integer and we are trying to insert a string. So Ctrl Enter. And again an error, but the error is different. The value 1 of the type string cannot be cast. So it seems that we have an error because the schema mismatch has been detected, but nevertheless Databricks is smart enough to try to cast the value 1 into the integer. So if we will try to write it like this, so still a string but pure number inside, this way we will be actually successful. Interesting. And let's look on one more example. If we remember, the first type of the first column is integer, meaning I don't remember what's the maximum value for the integer, something around 2 millions. This value is definitely larger than the maximum value of the integer, and let's see what will happen in this case. And again, it will detect that this is the big int, and we are trying to fit it, squeeze it into the int, so we get an error. So schema enforcement works, and I can confirm it. Now, let's talk about the schema evolution. And to be precise, let's try to write a record with Python, something what doesn't match the original schema. So here I have a simple data frame. It's a data frame which is having the 4 columns. The type of the 3 first columns is correct, but we are just having a 4th additional column. If we would use df write option and merge schema and then mode append and target table, this should allows us to expand our schema. Let's see if it works. And we should now have 4 columns because of this merge schema true. Let's verify it. And that's correct. We have successfully entered the 4 extended row. But there are limits of the schema evolution. There are limits of what we can do. So let's try to repeat the exercise. Just this time, let's try to change the type of the column from integer to string. So everything just like before, just we are now here changing the type of that column, and I will hit Ctrl Enter. So we are going to see that even with the merge schema equals to true, it's not wildcard. You cannot do whatever you want. It just allows you to expand the schema, but you cannot do the things like changing the type of already existing columns. If we would like to use or set up a schema evolution in SQL, we need to set up the global variable auto merge enable to true. And after that, even in SQL, without specifying, just like in Python, merge schema equals to true, even in SQL, we can expand our existing schema, and we are getting a table with 5 columns. Like just that. And one more thing before we will close this notebook. What if we would really have a need to change completely the schema, like changing the type of the column? There is such an option. It's called overwrite schema. So in this example, we have 3 columns And the first column, we are changing the type from integer to string. So we are trying to do something what we saw that previously was not possible, even with the merge schema. Just this time we are using option overwrite schema equals to true, and the mode overwrite instead of append, and Control Enter. And what we are going to get as the results, we are going to overwrite completely the table. So not necessarily frequently useful, but if you have a special case and you need that option, it's here. That's it for that notebook. Time travel. I love time travel feature. So whenever we are talking about the time travel, we of course are obligated to talk also about Back to the Future movie. If you are one of very few people who haven't seen the movie, you need to watch it. It's great. Okay, so what is this time travel feature in the Delta Lake? So basically this is a capability delivered by a Delta Lake which allows us to query or restore the previous version of the table, even the one before insert override. And to do a time travel, we need two things. Well, first of all, we need to have a Delta log, and we need to have, of course, parquet files with the data. Without parquet files with the data, there is nothing to restore. But even if we have a parquet files with the data, but we don't have a Delta log, we wouldn't know which data is still valid and which not, so we need really both. Now, the problem is that, as we could see, the Delta log and unnecessary parquet files can become really heavy, and if we would maintain it, if we would keep it without a time limit, this can basically explode our storage. Therefore, we have a two mechanism, which is somehow a limitation for the time travel, of limitation how much in time we can move back. But from the other hand, those are really unnecessary to have, which controls how long the Delta log is being stored and how long we keep unnecessary parquet files. The first one is called log retention duration, and the default value is 30 days. This is to say how long by default the Delta log is being stored. And the second one is deleted file retention duration, which by the default is set up to 7 days. And this one is actually being used by the utility, which we are going to see in a second, which is called vacuum, and it's really important. Okay, and surprise! I haven't found any lake in the Back in the Future movie. The most famous water which I found is this one. And yeah, and actually this is not a skateboard. I think it's called a hoverboard. It's really cool. And welcome in the new notebook dedicated for a time travel. Very cool feature in the Databricks Delta Lake. So at the beginning, let's set up the stage by creating a simple demo table and inserting couple of records. But the only reason for us of inserting the data to the table is so we can later on delete it. Like here, delete from demo will remove all the data. And now whole company is in panic, everyone is trying to figure out who did it and why, so they run a described history, and they can see that operation delete has been run by this guy. But it doesn't help a lot, the data has been lost unless somebody knows how to do a time travel. So by the now, looking on our previous notebooks, we already know that whenever we are deleting a data, this is not being removed. Actually, there is only appropriate entry in the Delta log created. Additionally, maybe deletion vector, additional parquet files can happen, but the data are still in the storage. And if they are in the storage, we should have possibility to at least query it. And the easiest way of querying the past data is to use a select star from table and then add at the end at v like version and the number of the version which we wanna query. If we take a look on our table with the history, we see that commit number 4 was at the delete, so the version which we really wanna query is the number 3. So let's hit Ctrl Enter and let's see what will happen. And here we have the results, which are exactly the same as the one before running a delete. We can repeat the same exercise in Python, also in very easy way. Spark create option version as of 3, Ctrl Enter, and the results will be exactly the same. Moving forward, we don't necessarily have to use the number of the version, we can also do the time travel using a timestamp. So coming back to the table with the history, let me grab the timestamp of the version number 3, Ctrl C, and let me just put it over here. I'm leaving Z at the end, Z stands for Zulu, Ctrl Enter, and again the results are the same. And if we can query a data from the past, it means that most likely we can restore a table very easy. And here comes the utility, which is very handy: restore table, table name to version as of 3. We could also use a timestamp. And now we don't even need to have to use add v3. The crisis has been managed. Okay. If we check the history, we will see everything what happened. We see that restored has been run on the table and when and by whom. Okay, so we know that we can do a time travel, mostly because Delta Lake doesn't remove a data. Parquets with the data are still there, but if we would maintain those parquet without any kind of limit of time, our storage would grow to the limit when it would not be any longer acceptable. And here comes additional utility, which is very dangerous, but at the same time very much needed, which is called vacuum. And vacuum delete unnecessary files from the storage. By the default, if I will run vacuum table, it will remove unnecessary files older than 7 days. And the information about the 7 days, it's important. It's a frequent questions on the Databricks exam. So let me run it. And in our case, we are just playing around. This is not a production table, but on the production table, it's very important to use at the end of the vacuum dry run. The reason being is that once you will delete some files with vacuum, those will be gone forever and you will limit your possibility to do the time travel. Adding the dry run allows you, before removing any files, see a files which will be removed. And in our case, first of all, the table is fresh. Second thing is that we just run a vacuum, so there is no list of the files, but we are going to see that in a second. But otherwise, always add a dry run. And depends on your environment. It's particularly important because those 7 days which we are discussing, this is something configurable. It can be configured globally or it can be configured per table, so you never know. Here for the example, I'm running vacuum with the information that I want to retain 0 hours. I can configure days, like retain 1, 2, 3, 4 days, or I can go wild and say retain 0 hours, and this is the most dangerous, the most edge case, where I'm saying that I don't want to have any history, remove all unnecessary files, I don't care how old they are, and here I definitely want to add a dry run. Just in this case, fortunately, there is a safety mechanism which will kick in and I will get an error with the information which is hidden. I need to expand this, that please use value not less 168 hours. So by the default, Databricks and Delta Lakes blocks me to do the vacuum on the time shorter than 168 hours. If anyway I would like to proceed, I can change it, this safety mechanism. Let me just scroll down through the log, and I can set up Spark Databricks Delta retention duration check enable. I can change it to false. Control Enter, and if I would repeat the exercise, this time retain 0 hours would be successful. What we can verify by doing a simple experiment. I will insert one row to our table, insert into demo values 9 vacuum, and straight away I am deleting that data, this row. And we already know that this will create unnecessary parquet file, which is pretty fresh. So if we think about the 7 days, it shouldn't be removed, but now we have opened a door to do the vacuum with 0 hours. So let's check if it works. Let me write vacuum table retain 0 hours and at the beginning dry run, and we should see at least one file to be removed. And here it comes. We get a list of the files to be removed. So the parquet file as well as deletion vector, which has been assigned to that parquet file. And now once I will run vacuum demo retain 0 hours, those files actually will be removed once forever. And done. So this operation actually is pretty slow and the files will be removed, but not necessarily immediately. It can take some time for a storage to process your request, but sooner or later they will be permanently removed, which we can verify by checking the history. Well, actually that's not a verification of the successful action, that's a verification of what history we see. So at this stage, we are going to see a list of the history. That's because vacuum deletes only the snappy parquet files with the data. It doesn't delete a data log. The data log are being automatically deleted by a Delta Lake Databricks after 30 days, but vacuum it's only removing snappy parquet. So we are going to see here a full history for the time being, which doesn't mean that you can do anymore a time travel, because if we run a vacuum and if the underlying parquet files with the data has been removed, we will not be able to do a time travel. We need both. We need delta logs and we need to have a parquet files for the time travel. So let's verify that statement, trying to do this time and time travel to, let's say, version number 2, like here, select star from the table, add v2, control enter. So actually this one was successful, and this is a good example. This one actually was successful, and the reason being is that vacuum has removed the files, but not the files which are mandatory to travel to this particular version. But if we would look on the history of the data, and this is the moment where we were adding the record, which later on has been deleted, and we run the vacuum. So if we would like to do the time travel to the version number 8, this time we will get an error. I'm 99.999% sure. Whew, good. First time I'm happy that I see an error. So the reason for the error is because we ran the vacuum and the data has been removed. So you see that is pretty interesting. You don't lose the whole history, you can lose a part of it, because vacuum doesn't delete all the data, it's remove unnecessary data. Okay, and talking about configuring the days per table, that's the example of how you can configure what is called deleted file retention duration. So if we will set up this to 14 days, then the default behavior of vacuum would be to delete unnecessary files older than 14 days. Okay, and we can verify if it has been applied by running describe extended and the table name, scrolling to the down, checking properties, and over here we see our property which we just set up. That's it for that notebook. And here comes the summary of the commands used in that notebook. Cloning. Cloning is basically about creating the copy of the table, but not a simple copy like create table as select star from another table, but also copying a metadata and sometimes the data. And in the Delta Lake, there are two types of cloning available. First one is called a shallow clone, which is a kind of light clone, which copy mainly metadata, and the second one, it's deeper, it's called a deep clone. We are going to see it in action. You can read the slide or you can wait for the notebook. And here we have a Lake Como, best known for its luxury villas. Looks nice and looks expensive, Italy. And we are now in the notebook dedicated to cloning data in Delta Lake and Databricks. Let's at the beginning create a source table which will be later on cloned using two different approaches. So the table is called source and we are inserting some values, deleting, updating, as well as adding the constraint. And once this is done, we can go further and create a deep clone, which is very easy. Create a table and the name of the table, deep clone source. A deep is optional, without deep it will also create a deep clone. Let's hit it, and usually this is a type of the cloning which will take more time because it copies metadata plus underlying snappy parquet files, so it should take more time. Here we have some statistics about what has been done, and if we check the history of that deep clone, this is a first thing worth mentioning. We don't have a full history of the source table. We have a history of that clone, and the first information, the first operation is cloning itself. We can go and check some operational parameters, not so super important, and operational metrics, but really nothing more. And then if we go and see details, we have a path to the place where the data are being stored, which we are going to explore it in a second. And we also have here in the properties the important information that the constraint has been copied as well. And that's a difference between doing a clone and doing a create table select star from another table. If you do a select star from another table, you don't copy all the metadata like you don't copy constraints. With cloning, you are more robust, you go deeper. So we can move back and browser and see what's in that location. And what we see shouldn't surprise us. We see a deletion vector because we have done some deletion in the source table, and then we see the parquet files with the data. So the question is, what will happen if we will insert a new record into the source table? And then we of course query our deep clone. What will be the outcome? Control Enter, and the answer is nothing. Clone is a snapshot in time. Depends on what type of clone you are doing. It's grabbing different part of the information from the source table, either only metadata or metadata and a data themselves, but from the specific moment in time. So we don't have in the clone the record number 5. Now, what would happen if we would go more aggressively and decide to delete all the data from the source table? And this is not an obvious question. So we are doing a delete from a source, and then we are doing a very aggressive vacuum, and we are querying a deep clone. And as we can see, the deep clone is as it was, nothing has changed. And here comes the whole story. The deep clone takes more time, it takes more storage because it copies all the data, but it cannot be touched by modification of the source table. So that's the benefit of the deep clone. Okay, let's take a second approach to cloning a data and starting fresh, recreating the source table as we have deleted all the records. But this time we are doing a shallow clone. The syntax is very similar, just we are changing the keyword deep to shallow. Everything else remains the same. We can browse the history of shallow clone, and again we see that the first operation was cloning. We can check details of shallow clone, and here we have again the location. We have a property, so we see that also in this time the constraint has been copied. And we can also query the location where the file is located, but this time location is empty. Then that's because the shallow clone doesn't copy the data, it copies only the metadata. And now again, the same two questions as we ask ourselves during a deep clone. What will happen if we insert a record into the source table? And then query shallow clone, of course. And the answer is exactly the same, nothing, because again, a snapshot of time. But what will happen, team? What do you think? What will happen if we delete all the data from the source table and then we do the vacuum and try to query our clone? What will be the outcome? And we get an error. The reason being is shallow clone relies on the data in the source table, period. It's faster to do. It's cheaper because it doesn't consume so much storage as a deep clone, but it relies on the data of the source table. That's it for that notebook. And here comes the summary of the commands used in that notebook. Change data feed, super important feature. And well, the reason why it's important is, as we saw with the delta log, we track those data set level changes, like, hey, here is a file with the new data, or hey, this file with the data is not any longer valid. And yes, we have the deletion vector, which tracks more row level changes, but this is really for the Delta Lake internal use, not really for us. What we have for us, it's called change data feed. And with this feature, we will be very easily able to track and query the records which has been inserted, updated or deleted, and we can use it for different purposes. There is really many use cases, like for instance, we can process only the records which has been updated. We can have a more granular audit log, or we can optimize our pipelines. Sometimes when we have a batch process, we don't have a need to read whole data set every time. We want to read only the data which has been inserted, or only the data which has been deleted. But anyway, we are going to see it in action. And here we have a lake Titicaca, the world's highest navigable body of water, Peru, Bolivia. And we have a new notebook, this time about change data feed, super important in Delta Lake Databricks. So that's the way we could turn it on for all the tables in our environment. We will not do that, we will go by the table. So at the beginning, let's create our target. It's called again demo, and we are inserting a couple of records. We are beating that demo table a lot now, but okay, let it be. And we can query quickly a folder with the data just to remind ourselves a structure. And now we go and turn on a change data feed for this particular tables, alter table, set properties, and it's done. Now, very important, we will perform 3 operations on that table. First of all, we will insert a couple of records, then we will update some of it, and then delete. And we are deleting ID number 2, which is Spider. No, I don't want to delete Spider. Let's change it. Let's leave Spider alone. Control Enter. And all those 3 operations were performed with the change data feed enabled, which means that if we look into the folder now, we are going to see additional subdirectory _change_data, and let's check what's inside. And we have some parquet files over here. Okay, so the change data feed is being registered. Now, how to query it? Maybe first of all, let's display the history, which will be important for us. And we see here a couple of options. Version 2 was a version when we changed the properties of the table to capture change data feed actually. And the way to query it is to use a function table changes, which as the first parameter takes a name of the table and then a version starting from which we want to see a changes. So let's select start from this one, and here it comes. This is our change data feed, meaning almost in the real time we get segregated informations about what has changed in the table. And we have update. For update we are going to have two records, pre-image and post-image, meaning what was the value of the record before updating and what was the value of the record after updating. Then we have the information about the inserts and we have the information about the record which we have removed. So you can see that with the delta logs we can track a table level or the file level changes. With the change data feed we have a view on the row level changes, which is super useful, and there is many use cases around it. We will be talking about change data feed way more during the streaming movie, but even though, let's still implement one frequent simple use case. And here it comes. So let's say that we want to send deleted data to another team, I don't know, maybe to audit, maybe to some other colleagues, and to be precise, into the table which is called demo deleted data. And of course in real time as much as it's possible. So first thing is we will create a table demo deleted data with only two columns, ID and string. So we will be after identifying what has been deleted and the name. So let me create this one. And here we have a simple stream. We haven't spoken about streaming yet, but this one is fairly simple. We are reading a stream with an option read change feed true, starting version 2, just the same as above, from the table demo, and here we are doing some filters and select. So basically we are filtering change type delete, so that's this column, so we are looking only for the deletes. And we are selecting ID and name. So if I again scroll up, so we are selecting only those two columns, okay? And moving forward, we are sending or we are writing this data, appending it to this table. And we need to have a checkpoint as something standard whenever we are doing a stream. So again, we are monitoring the demo table, looking for the records which has been deleted. Whenever we identify that record, we want to append it to this table. Okay, let me run a stream. Our stream is up and running. And here we have the statistics. So it looks like one record has been processed so far because we have one record deleted already in our change data feed. If we look into the target table, demo deleted data, we should have one record. If I remember, it's Mickey. And now let's do a small experiment and delete from demo table another record where ID equals to 3. And it will take 2-3 seconds for the whole stream to process it. Meantime, we can check in the change data feed if we have already this deletion recorded. So it has been recorded. Okay, we hit a tiger. Okay. So it has been recorded already in the change data feed, and let's now check if the demo deleted data, if it has received a data about a tiger being deleted. Yes, so as you can see, it works close to the real time. So that's one of the use cases of the change data feed, but there is more. Basically, this is very useful mechanism. Okay, and what else? So what we should know, what we should remember is that we can query a changes not only by the version of the table, but also by a timestamp. I will not do that, so it's pretty obvious. We can also set up a range of the timestamp. So we are looking for the changes which happened between this day and this moment and this day and that moment. Or we can do a range by a table version like 5 and 7, which is over here. Okay, that's it for this notebook. And here comes the summary of the commands used in that notebook. From now on, we will start exploring the topic of optimization. And of course, a delta log by itself, it's a great optimization feature, which solves many of problems and it helps a lot, but there are things which we can do on the top of it. And we will start learning this topic by investigating the problem of the small files. We can imagine that we have a data set, even 1 gigabyte, in the huge number of the small files. And then we fire very broad query like select average from all the data you're having in the table. So Spark will need to go through all the data, and most likely it will create one task per each file. We are going to end up with very long job. So typically we will be after consolidating a small files into the smaller number but bigger files. And no matter how simple it sounds, there are actually many approaches we can take. Like for instance, one question we can ask ourselves is which of those small files from the left put together into which file on the right? That's one of the questions. And in this notebook, we will start with learning a basic command, which is optimize, which will perform very basic consolidation of the small files. And here we have amazing lake in Canada, Peyto Lake. In this notebook, we are starting a big and exciting chapter of optimization in the Delta Lake and Databricks. And in the next couple of notebooks, we will be looking on the different approaches, different techniques, how to attack that topic. Before we will do that, let's start by building a basic understanding what are the common problems we can face using a Delta Lake. And we will start with very famous one, the problem of the small files, and then we will perform a basic optimizations to deal with it. So, at the beginning, I will turn off auto optimization in the Databricks Delta Lake. We will explain it in the next notebook actually. And then I will create a table which will be dedicated for a small files. And what does it mean? It means that shortly after that we have our for loop, which we have seen before, which in this case will perform 200 operations, each of it ending with the commit and each of it saving a data to the different Parquet file. So we are going to have a table with plenty of small files. And once this is done, we can check the history just to make sure that we have a number of small commits. And here it comes. You see every write, every insert has generated a separate commit, and we have a separate file for each of that commit, both delta log as well as Parquet file with the data. And if we run, actually before doing the select, if we run describe detail and small files, we are going to see that we should have something around 200 files with the data, which is over here. Okay, so now let's do a simple query like this one. Select from the table. Just in my case, in our case, I am using the function average. And there is actually a reason why I'm using this function. It's because we need to remember about the delta log, which is having the statistics about the column. If I would do mix or max or other function, Databricks can figure out in which file the data is without reading it, so it would optimize the query by itself. With average, I'm very much forcing Databricks and Delta Lake to go through all the files. It was very fast, that's okay, we will get back to that query in a second. Before we will discuss it further, let's now create a second table dedicated for a big file. So this is a table creation, and over here I have the same query, just this time there will be one commit. We are inserting all the values, here is a for loop, we are inserting all the values at once, it should be very fast. And if we run describe detail right now, describe detail and a big files, and we check the number of the files on the right, we have only one file, which we can also verify by querying the folder at the same result. One Parquet file with all 200 rows. And now we will run exactly the same query, select average from a big files table. And because of the data is small, we may not see a difference at the first glance. This query took 1 second and that's the results. And the query on the small files table, okay, this took 4 seconds, but it could be coincident. To truly understand the difference between querying a small files over here and querying a single file over here, we need to go to our favorite, Spark UI, exactly. And if you still don't know Spark UI, you need to watch Introduction to the Spark Architecture. We are explaining it there in pretty much details. Okay, so let's go to the SQL data frame, because everyone who watches Introduction to the Spark Architecture knows that whenever we are using a query, we are using a data frame API. And now let's find our jobs. I need to scroll it down. And our jobs are over here, so let's get here. And let's remember that we are now talking about querying a small files. So if I scroll down and I find the number of the files which has read, it's 200. And what is more important for me is a scan total time. So how much time in total all the tasks spent on reading the data from the storage. And here I have over 5 seconds. Over 5 seconds spent reading this very small data set from the storage. Now let's compare it from the big table, and let's remember over 5 seconds. So now let's go to the same query from the big table, and over here job 1306. So the same procedure, finding this job, scrolling down, expanding, looking for the number of the files. Number of the files read 1. Scan time, and here you have a difference, less than 1 second. So that's a big difference of time which tasks consume reading data from number of the small files versus the data from one big file. Therefore, naturally, if our data set would grow, the problem would become bigger and bigger. Therefore, a lot of optimizations mechanisms in Delta Lake and Databricks are targeting the problem of the small files. And later on, the one more advanced is how to pack which data into which file. But that's we are going to show in the future notebooks. Okay, so once we have the problem with the small files in the small table, let's look on the very basic mechanism, how to optimize it. So I'm describing the history of this table. I don't remember why, but I remember why. Okay, so that's the latest history of that table. And now I will run optimize and the table name. Optimize and the table name. Optimize also accept additional parameters, but this is a subject for the future movies. Right now it's just a pure optimize without any extra options. And this has been done. We get some here interesting metrics. Let me expand it. And what we get here, maybe let's go to the focus mode. What I have here, number of files added 1, number of files removed 200. So basically what Databricks did, it has removed, or it has created a Delta log entry saying that, you know what, remove all those 200 files, they are too small, but I have added one big file, and in that big file you are going to find all the data you are looking for. Period. Simple. So optimize, very useful. And as we are going to see in the future, Databricks will be firing optimize for us periodically as well. And now if we check the history, we are going to see optimize as the last operation. And the last thing for this notebook, let us repeat the same query on the same small files table. And it was visibly faster. And now let's go to the Spark UI 1325 SQL data frame. 1325 here, scrolling down. Okay, and in this case, after optimizations, the same query has read one file and has spent significantly less time on reading the data. Okay, that was the demonstration of the small files problem and basic optimization. That's it for that node. What we saw before was a kind of manual optimization because we needed to run optimize commands by ourselves. In the Delta Lake, there is also a kind of a semi-automatic optimization. Semi because we need to turn it on, and there are two features which we are going to show in a second. And in the Databricks Premium, there is also something what is called predictive optimization, which I'm going to show in a couple of minutes. So, talking about this semi-automatic optimization in the Delta Lake, two features actually. The first one is called optimize writes. Traditionally, on the left, when executor finishes its job and it has a result, it will try to save it to the disk, to the file by itself. With the optimize writes, Spark will try to get those results from the executors and consolidate them before writing to the disk. Smaller number of writes to the disk, a job is faster. And the second feature is called auto compaction, and if we turn it on, it will automatically kick off optimization commands for us. Every time it will detect 50 small files or more. 50 is by the default, but we can change it. And in case you are using a Databricks Premium, you still want to know those features, even because they are asking about it on the Databricks Data Engineering Certificate. But most likely you want to rely on the predictive optimization, which we will discuss in a minute. And this huge blue thing which you see in the middle of the screen, it's so big that it's typically referred as a sea, but technically it's a lake, Europe-Asia. And we are now in the shortest notebook about auto optimization to see how auto compact impacts the file layout on the storage. And that's the way we can turn it on for the whole session. So Spark Databricks Delta Auto Compact Enable equals to true. All those parameters names are super long, that's how it is. And then we can check another important setting, meaning what is the minimum number of files of the storage, minimum number of the small files of the storage for auto compact to kick in. And it's 50, default value. So to demonstrate it, we will do what we were doing a couple of times already before. We will create a table for a small files, and shortly after that we have well-known for loop, which is creating number of commits and number of the small packet files. And once this is completed, we can go straight away and check the history, what was happening under the hood. We will of course see the number of the small commits, as this is something what has been triggered by us. Let me scroll down to the beginning of the history. And here we have the number of the small commits, which are identified as write operation, but somewhere around 50 files we will have optimized kicked off automatically for us. And operation parameter, if we extend this, then we have information auto true, meaning that it was automatically fired by the Databricks. And going further and further details, yes, so here we have the number of the files which are being removed and number of the files added. Okay. Do we have any other optimization here? Let's scroll up. And we have another optimization which happened after another 50 files and the same story. So here comes the auto compact in action. That's it for that notebook. So talking about the Unity catalog predictive optimization. Whenever you are using the Unity catalog managed tables, Databricks Workspace Premium or above, SQL Warehouse or Databricks Runtime 12.2 is being used by you or above, and whenever there is a predictive optimization is enabled on your account level, then a Databricks will kick off those two optimizations for you. The first one is optimize, the second vacuum. So whenever we are going to see it, just don't be surprised, it's Databricks trying to do something good. Let's talk about more advanced optimization techniques. And whenever we are choosing the optimization techniques in the Delta Lake, which we are going anyway to discuss in the next couple of notebooks, extremely important factor is a data cardinality. And we can have a data, meaning columns in our table, having a different cardinality level, starting from the low cardinality, through medium, high, and or having even extremely high cardinality. And what we mean by the cardinality is the number of different possibilities of the values in that column. For instance, if we have a column which takes as the value only day or night, there are only two possibilities for the value of that column, and this is the low cardinality. If we take payment type, well, how many different payment types we can have? 5, 10? Or if we take a date, but only a year, it's also a low cardinality. Then if we would take a day, year plus month, the cardinality goes up. And if we take a year, month, and day, the cardinality gets even higher. And if we have a text field, the possibility of having the same value in different rows is very low, and this is extremely high cardinality. And this determines effectiveness of different optimization approaches we can take in the Delta Lake. If we think about the low cardinality medium, then a classical solution for that is a partitioning, which we are going to discuss. You cannot efficiently apply partitioning for the high cardinality columns, because then you would create a problem of the small files. You would over-partition your data. Another optimization technique which we will investigate is called Z-ordering, and this is primarily targeting the high cardinality columns. You can apply it to the low cardinality and medium, but you will not see so much benefit as when you would apply to the high cardinality. And then we have something what is dedicated only for the extreme cardinality columns, which is called Bloom filters. It's really cool, we are going to see it. And we have a new kit in the blog, liquid clustering, which we are also going to discuss. And if you ask at Databricks, they will tell you that it's the best thing after sliced bread, and basically this is solving all the issues. And indeed, it's really smart, really cool, but how great it is, that's something what we are going to see. Partitioning. In the documentation, they are referring to it sometimes as the Hive style partitioning. So let's take following table. Those are some transactions. We have a column with ID 1, 2, and then we get a timestamp, price, category, and location. So before deciding to partition our table, we need to answer ourselves a couple of questions. Well, the first one is if the table is big enough. And the basic recommendation from the Databricks is do not partition the table which is having less than 1 terabyte of data, because you already have optimization mechanism in place like a delta log and you may not see the benefit. The second question is, once you will decide to partition your table, make sure that each and every partition is having at least 1 gigabyte of data, as the larger partitions seems to overperform as small partitions. And then the next question is really about choosing your columns efficiently. Once you will choose your column, it shouldn't be only the low and or medium cardinality one, but you should have also an equal distribution of data. So let's say that we choose as for partitioning the column category. Well, without seeing a full table, we cannot be sure that if it's a good idea. It can be that 99% of things which are being sold in that store are electronics. And it doesn't make any sense to use that column for partitioning, because 99% of the data would be in one partition. The same can go for the location. Majority of the sales may happen in New York, and this column will be a wrong choice. Frequently, a blind assumption, pretty good guess, is to take some sort of the date for the partitioning column. Like in our case, we have a timestamp. And for instance, we can take this part of the date, year and month, create a separate column and use that column for the partitioning purposes. And then if we look on our storage, what will happen is that we will still have one delta log on the root level, but for the data for the Parquet files, there will be a separated subfolders created, like in our case, year and month, and in those subfolders we will have a Parquet with the data. Or it may be that your table is so huge that choosing one column it will not fly, and you might want to choose two columns. That's also possible. So here we choose a date, year and month as one column for the partitioning, and then we have some column 2 as the second dimension for the partitioning, and then we are creating a subfolders in subfolders, which is having its own challenges, and one of the challenges is a data distribution. So if we would assume that all those cells represents a subfolders, like in our case, and this is a real life situation, we may have some subfolders which are completely empty, and in some folders we can have multiple files with a significant volume of data. We can try to overcome that by doing some kind of the range partitioning and saying, you know what, the column 2 is good, but it doesn't make a sense to create a separate subfolder for each value, 1, 2, 3 and so on. It may be that what will make sense is to create one subfolder for the value between 1 and 4 and the second subfolder for the value between 5 and 8, like over here, and then the data distribution looks significantly better. And crater lake. Who would guess that we can have a lake in Volcano? USA. Alright, let's start a notebook dedicated for the partitioning. It's not going to be long, but it's going to be important, as partitioning is not so crystal clear if and when it's beneficial for us. So at the beginning we will do a small setup, as we will be doing a query comparison, so we want to turn off caching. And now in this notebook we will be working on the data about the airlines, which are fairly significant in size. So here we have 127 megabytes, 5 gigabytes and so on, and they are available in the default Databricks datasets. So if we look inside onto one of it, just to get a feeling of type of the data we will be dealing with, we are going to have here some year, month, day of month, departure time, and moving forward from the columns which we will be using, we have the columns like origin or destination. Okay, so at the beginning, let's create a table, but this one will be without any partitioning, and this is called flight data, and that's a schema, very simple. And let's ingest 2 years data about those flights into this table. And now let's create a similar table, just this one will be partitioned by year. So we are adding a keyword partitioned by year, and the name of the table is the same. At the end we are adding a year, just so we can recognize it later. Control Enter, and then we can describe that table using describe extended, and we will see the information about the partitions somewhere over here, scrolling down, and here we have it, partition information, and the column which has been used for partitioning, it's of course year. Now let's repeat the exercise and ingest the same data into this one. And now once we will look into the folder with the data, what we are going to see is that we have a separate subfolder for each partition. In our case, we have partitioned by year, and we have ingested only 2 years data, so we have one folder for 2007 and one folder for 2008. So here it comes. You see how partitioning is doing the physical separation of the data. So it's changing our file layout. Now let's do a small comparison between the original table without any partitioning, flight data, and the flight data with the partition over year. And this is important because we will see that it's not so black and white, that the partitioning is always bringing the benefits. So right now I am firing the flight data query, and now on the over the partitioned table. And let's go again to the Spark UI over here to see how many files has been read if we are looking for the year 2007. So SQL data frame and finding our query, it's over here. Scrolling down and looking for how many files has been read. This is the first query, flight data without any partition. Number of the files read 6, not so many. So 6 without any partition, and let's now check how many files has been read with the partition. The same procedure, just finding different entry and looking for the same number. So we scroll down, and suddenly we see that the number of the file is also 6, the same number of the file. So what is happening over here? We would expect, if we query over the table without the partition, the number of the files which we read, which we go through to find 2007, is larger than when we go and when we look only for that year through the table which is partitioned over the year. Correct. But not in case of the Delta Lake, because we need to remember about the Delta Log, and the Delta Log themselves, without any partitioning, already has the information about the statistics. So using a Delta Log, Databricks, without any partitioning, can sometimes already figure out in which files the data are, and it will not blindly go through all the files. Therefore, and I'm not saying that partitioning is not useful, it is, but just sometimes the value of the partitioning or benefit of the partitioning is not so obvious. Therefore, it's not a silver bullet for all the performance issues. Now let's see another thing, another case. Here we are again creating the same data, just this time we will partition that by 2 columns, by year and by the origin. And we are changing the name of the table so we can recognize it easily. And let's ingest the same data into that new table. The first thing worth mentioning, that ingestion data to this partition by 2 columns table took almost twice as much time as previously, because the data needed to be separated, splitted between the folders. And if we look into the folder of previously existing partition into year 2007, we will see further subfolders per origin. So here we have the first column which we use for the partitioning, and here we have the second column which we use for the partitioning. So we have many folders. If we have many folders, we can potentially also have a problem of the small files. Nevertheless, let's go further and do the performance comparison of the original flight data without any partitioning, and we will be looking here for a year and for the origin, very specific, and calculating the average distance. And then let's do exactly the same query over partitioned by 2 columns table, and let's see if we are going to see some difference. So the result is the same, good, that's obvious. And then let's see into the Spark UI how many files we have read, and we already know that we can get exactly the same number because Delta Log is there in place for us. And even without a partitioning, the data log is providing huge value, 7172. So that's the one. How many files? How many files? Are we going to see a difference? So without any partitions, so here we have read, number of the files read, 6 again. 6 files have been read. And now let's check how many files we have read when we were querying the table partitioned by 2 columns. Job 73, 74, 75, and it's over here. Scrolling. And how many files? How many files? Who knows? Number of the files read, 2. Okay, so now once we partition the table by 2 columns, here Yes, we can see a significant difference. The delta log was not capable to identify those files so accurately compared to the scenario where we use the partition by 2 columns. So here we see the benefit of partitioning. Here we are reading indeed less files, but at the same time, due to number of the subfolders, we are exposing ourselves to the problem of small files. Okay, let's move forward and let's see actually how many files we have. So how many files we have for the table without any partition, and we will use describe detail, and we have 12 files in the original table. If we look on the table which is partitioned by 1 column, here we have a number of the files, it's still 12, okay, still 12, and I'm checking the good table, yes, I'm checking good table, and if we check the table partitioned by 2 column, I'm betting that around 100, but just my bet. Number of files, 3,371 files. Huge number of files comparing to the size of the data itself. We have around ½ GB, a bit more of the data. So we need to remember about what Databricks is saying. Well, first of all, if we read between the lines, they are never saying that the partitioning is a silver bullet. And second thing is that they are saying that if we are partitioning the table, we should partition the table which is at least terabyte in size, and each partition should have at least 1 GB of data. Let's do at the end one more thing. Let's see actually the distribution of those files of the table which is partitioned by 2 columns between the folders, just for fun. There is no value in that, we are doing that just for fun. So here I have a small query which is figuring out how many files there is in which subfolder, and once the results are done, this is a distribution, number of files per folder. So we remember that we have 2 dimensions, a year and the origin, and this is a number of the files in which subfolder. So we see that we have a subfolders, some num files with the number of the files 6, that's for the origin ADQ and the year 2007. On the other hand, we have those white spots, it's hard to point out to this, maybe over here, where we have less number of the files. Like in this subfolder, we have only 2 files, and here again 2, 5, and of course, so it's one of the challenge with the here one. So it's one of the challenge with the partitioning to choose a columns over which we are going to partition, to have equal distribution of the data between the subfolders, to have equal performance depends on the query. So in this case, you know, if we would be query over the origin ISO 2007, we would get a better performance than if we would query over this origin because there is less files. And let's take a look on something else. Let's look on the volume in megabytes of the data in each subfolder. Previously we were looking on the number of files, here we are looking on the megabytes, and this is also interesting. So you see that probably in average we have 0.3 megabytes of data in each subfolder, very small number of data, and we have some subfolders which is having 4.6 and here 7.2. So doing the partitioning properly, it's really tricky, and only by the fact that we are doing the partitioning on the table, it doesn't mean that automatically the benefits will be visible for the end user, because we have a delta log. That's it for that notebook. Couple of points to remember when it's going about the partitioning. Well, the first one is the benefits of partitioning are not always so obvious, especially that we are working with the delta lake, which is having already a built-in data skipping mechanism with the delta log. Then the second thing is, the second problem is that if the usage pattern change, meaning if the users will start using different columns in the queries, then the partitioning needs to be changed. And the thing is that whenever you want to change a partitioning, you need to rewrite the whole table. Another problem is that when you choose a column, you can get a data skewness, so you need to really pay attention on which column you choose. And whenever you are choosing especially more than one column, you need to be sensitive on the problem of the small files. So the generic recommendations from the Databricks is do not partition the table which is having less than 1 terabyte of data, and whenever you are partitioning it, pay attention to have a partition with at least 1 gigabyte of data. And here is a summary of the main columns used in the previous notebook. Let's talk about the optimization technique, which is called z-ordering. And well, first of all, what is already obvious from this slide, it has been inspired by Zorro, what we are going to see in a second. And the second thing, the whole idea is about how to choose which rows put into which file. So, and it tries to do that a bit in a bit more clever way that we have it in the partitioning. In partitioning, it's very simple. If the value is following, go to this file. In the Z order, it's a bit more clever. And to understand a Z order, let's contrast that actually with the partitioning. So let's say that we have a table and we have two perfect columns for the partitioning, column A and column B. Just in case of column B, we have decided not to create a separate partition, separate subfolder for the value 1 to 3 and so on, but we decided to go with the range partitioning. So exactly as we have seen in the partitioning section before, and create a separate subfolder for the value 1 to 4 and 5 to 8, and pack all the data into those subfolders. And actually the volume of the data in our table is just perfect, and each of that subfolder is having exactly one file. So we are ending up with having 16 files perfectly the same in the separate subfolders, and those files are represented by this red shape. Well, Z order is a bit different. Well, first of all, it will not create any subfolders for us, but it will take all the rows and figure out how to efficiently pack it together on the files, which will be located on the root level of our folder, the same level as our delta log is. And the way to figure out or to decide which rows should go into which file, there are two steps. First of all, it will use a Z algorithm to draw a line through the values in the following way. Like it will take a first value and merge it with another. Simple. But then it will go left, bottom, right, up, right, bottom, right, and moving down, and it will start repeating. What we can see that it's a Z shape, and that's the reason it has been inspired based on Zorro, and that's the reason why it's called a Z ordering, because it's using this Z-like algorithm to decide how to connect different rows together, in our case using two columns, column A and column B. And once it will decide how to connect the rows, then it will follow this line and decide how to split the rows into the files. So it will take 4 first rows and pack it into one file. Then it will follow a shape, it will follow a Z shape, and will take those 4 points and put it in another file. And those will be done in another file, another, and so on, as it will finish packing all the data into files. So what? We are ending up with having, anyway, 16 files, and there is no noticeable really difference visible. Okay, yes, the file looks a bit different. On the left, in case of partitioning, the files were like kind of flat, and here we have a square. Who would care? Well, so let's take, for example, that we have a following query, and I put it on the top. I didn't have any other place to put it. Select star from a table where column A is 4 or column B is 3. And let's try to run that query on the table which is partitioned and on the table which is with the algorithm Z order. And let's see how many files and how much data we actually need to read to return the results to the user. So, starting with the partitioning, column A equals to 4, it means that we need to read those two files, right? Simple. So we'll take a column A, value or subfolder with the values 4, and we need to read those two files, those two subfolders in our case. But then we have or column B equals to 3. So we need to read 7 more files. So in total, we are ending up with reading, and on the bottom we have a summary. We are ending up with reading 9 files. And in those 9 files, what we can consider as valuable is only the data in the blue shape, right? Everything what we have read in those files, which is not in the blue shape, like 1, 1, 1, 2, 2, 1, 2, 2, this is a false positive. This is a data which we have read, but are not valuable from the user perspective. That's not what user was asking for. Nevertheless, those data are located in the same file as the data which user is actually looking for, so Spark needed to read it. So we read 9 files and we had 21 false positives. Now, what is interesting is that if we would run exactly the same query on the table without partitioning, but with the Z order, we need to read those 4 files, of course, and then column B equals to 3 and additional 3 files. So we are ending up with actually reading only 7 files and having a significantly less a false positive. And that's of course the edge example. Not all the queries will have so visible benefit of the Z over partitioning, but in this case the benefit of the Z order is super visible. And here we have a shaped canyon. Yes, it's technically it's not a lake, but nobody is perfect. USA. So it's time to see how we can apply a Z order to our tables. At the beginning a small setup, and then we are going to load a similar data as we were loading in the previous notebook. Let's create a table which is a flight data. At the end Z stands for Z order, and then we are loading a bit more data than previously. And once the data are loaded, we can apply Z order, and we do that by using the optimized utility, the name of the table, and then Z order and the columns on which we want to apply Z order. Just in contrast to partitioning, the sequence of the columns doesn't matter. So if we would do Z order origin year or Z order year origin, the end result will be the same. And it's done. What is worth paying attention to is that time it took more time than actually writing a data to the table itself, and the reason being is that Z order, every time we do a Z order, it needs to rewrite all the data on the storage, so it's really expensive operations. Let's move on. If we describe the details of that table, we remind ourselves that we have here information about partitioning and about the clustering, but we don't have information about the Z ordering. So if we have a table Z ordered, it's not so obvious for a user to figure this out and to use a Z order efficiently. We can find out if the table has been deordered, going through the history, and then looking for operations optimized, and here we are going to have the information that it was optimized with the Z order, but this is not really handy. Regular user will never do that. So if you want a Z order, you need to Z order that in the background, hoping that the users will use the right columns for the filters, or just simply educate them. And then moving forward, just to check how the data looks like in the storage. So we have actually a couple of files, but the reason for having so many files is because I didn't run a vacuum. So let me run the vacuum, and this will clean up the data, and we will have only files created by the Z order available in the storage. And now let's list down the files in the folder one more time. This is also important. We are listing the files to pay attention to the size of it, because actually right now we have 3 files after Z order. So Z order has compact all the data in those multiple files into only 3 files, and the size of those files is pretty noticeable. Each file is more than 300 megabytes, so those are big files, guys. And if we look into the data log just to see how the Z order operations is reflected into the data log, and we grab the Z order commit, we are going to see that the Z order is removing a lot of the files, so those are the files which were present in the folder before, and it's adding only those 3 files which we just listed above. Okay, so another thing with the Z order is that we can change the columns over which we are Z ordering, just we will need to rewrite all the data again. So previously we were doing the Z order by, let me remind myself, so we were doing through the year and origin, and this time we are doing a Z order by origin and destination. Let's run it. So this one has been done as well, and here we have the results and metrics, number of files added 3. And if we go and remove the old files, and then we'll list down the files in our directory one more time, so we are going to see 3 files, and those files again will be pretty significant in size, but those are different files than the files before. When we had the different columns in Z order, we can compare it. Like 317, let's see if such a file was previously available into the folder, and 317, it wasn't there. Basically the reason being is Z order is rewriting all the data, and that's the heavy part about the Z order. While it provides the optimization, indeed, by packing the appropriate data together, it's really heavy operation to perform. Okay, and the last section in this notebook, it's something what is actually pretty frequent scenario in the production. It's a combination of the Z order and partition, meaning what we can do, we can partition our table and do a Z order inside of each partition. And the idea behind it, to avoid the small files problem, as we have seen a notebook before when we were talking about the partitioning. So the table has been created. Let's now load the data into the table and we will see how this works. And let's check out how the folder for the partition looks like before we will actually do any Z order. So that's a subfolder for the year 2008. We see that we have multiple files. And then what's interesting, we can actually do a Z order for a very specific year. In our case, this year makes the partition. We are making a Z order for the specific partition. And why this is interesting? Because it basically means that we can do a different Z order for a different partitions. We can imagine easily that there is a different search pattern for the current year and the previous years. And that's what we can support with the Z order. For the current year, we can choose different columns for a Z ordering. And for the past years, we can choose something else, depends how people are querying through the data. And let us just clean up the old files by running the old good vacuum. And if we list the files again in the same directory, 2008, we are going to see one file in comparison to the year 2007, in which we were not doing any Z order. So 2008, one file, and in 2007, still many of the files. We can of course change it by doing a Z order for remaining partitions as well. And this will bring the order to remaining partitions, which we can of course verify by cleaning the old data and checking the content of 2007 year, where we have only one file. That's it for that notebook. And the key takeaways about a Z order. So Z order is usually more efficient than partitioning. It helps to avoid over partitioning and it's usually more efficient in data skipping. Then more columns we use for the Z order, the larger benefit we are going to see. Typically, a good idea is to Z order over a high cardinality column. For instance, such as typically users are using in the joint statements. Nevertheless, we need to remember that those columns should be in the first 32 columns, so we have a statistics for them in the delta log. If we don't have a statistics for them in the delta log, no data skipping is possible, so the whole idea doesn't make sense. And optimization does not happen automatically. We need to run optimize. So if we add more data, we will not fully benefit from the Z order, or if we remove it, the same story. And as data change, we need to rerun optimize with the Z order. So that's what we just said. And what is very interesting is that we can use a Z order inside the partitions. And this is a summary of the commands which we have used in the previous notebook. Bloom filters. I like Bloom filters. Bloom filters are cool. To have a Bloom filters up and running, we need three things, and the same way it's a good illustration how it works and what is it. So the first thing we need to have a file, not a table, a file. We are talking about the Bloom filters per file always. So here comes our file with multiple columns, and one of it is a free text, or in our case email address like smith@gmail.com. Then the second thing which we need to have a binary structure which will be assigned to that file. And this is called a Bloom filter. This is a binary structure. In our case, it's having 9 positions, but of course it can be way longer. And at the beginning, all the values are 0. It's a binary, so the values can be either 0 or 1. And the third thing we need to have a hash function, and we will apply a hash function for each and every value in our column. And the hash function should return the value between 1 and 9 because our Bloom filter is having 9 position. So we take our column, which doesn't have to be in the first 32 columns like Z order. It can be somewhere at the far end of the table. We take a hash function, we apply it to each and every value of that column, and we get the information that, you know what, for smith@gmail.com, the value of our hash function is 3, for Johnson 827, and so on. With that information, with that value returned by a hash function, now we can go back to our Bloom filter, and wherever there is a value, on the position 3, 1 to 3, change a value from 0 to 1. And then Johnson is having 8, so let's go to the 8 and change it to 1 as well. Williams is 2, and we are ending up with our Bloom filter looking like this. Now, why this is useful? So let's say that user is asking about this, is making a query about this super high cardinality column like the email address and asking, hey, give me information about smith@gmail.com. Spark and Delta Lake are going to the Delta log, but the Delta log is saying, you know what, I don't keep a statistics for that column. First of all, it's like a crazy high cardinality column. Second thing, this is at the far end of the table. I'm keeping for the first 32 columns. So normally now, Spark would need to read each and every file one by one to find out if any of this file is having Smith value. But files can be really large, plus we can have a big number of files. Instead of that, with the Bloom filter, Spark can go to the Bloom filter, take a record user is looking for, like this smith@gmail.com, calculate a hash function, get an information that for Smith, there is a value 3 of that hash function, and check in the Bloom filter, okay, is a value 3 set up to 0 or to 1? Because if it's set up for 0, for 100%, the value I am looking for is not in that file. This is guaranteed. This is 100%. There is never a false negative happening. So it's going and reading that file, and it happens that it finds a Smith. Now a user is looking for, let's say, Kaminsky@gmail.com, and so Spark is taking a hash function, calculating the value, and the value returned it's 9. And we already saw a 9 before. So again, it's going to the Bloom filter, checking a field number 9. Field number 9 is set up to 1, and this is information for Spark that not for 100%, but most likely the value user is looking for is in that file. One of the characteristics of the Bloom filter is that you can get a false positives, and you may read a files which in fact doesn't have a data you are looking for, but that's a side effect. What the Bloom filter is really good at is eliminating a files to read. So if you get with the hash function that user is looking for spark@gmail.com and the hash function is returning a value 5 and the value 5 is set up to 0 in the Bloom filter, this is guarantee that this value is not in the file. And as we are going to see that in the notebook, for each and every file there will be a separate Bloom filter. And here comes another lake. What, you thought that all the lakes are blue? That's what I thought. Maybe I was suspecting that some of them are green, but definitely I was not expecting the pink one. Australia. Bloom filters in Delta Lake. So what we want to do in this notebook, we want to check how to create the Bloom filter, how to check if the Bloom filter has been created, and how to check if the query we are running is considering the Bloom filter at all. So at the beginning, a small setup, and this is a data which we'll be analyzing in this notebook. We already know that data about some flights. And at the beginning, what we are going to do, we are going to create a table, and on the top of the table, we will straight away create a Bloom filter index on the table, that's the name of the table, for a column flight ID. If we will take a look on this table, there is no such column like a flight ID. Basically, this table doesn't consist any useful for the Bloom filters columns. Therefore, I have decided that we are going to create one artificially. And in the table definition at the far end, we already have a flight ID. That's why I can afford to create a Bloom index on that column. And when I'm ingesting a data from about that flight, so here is the data ingestion. And when I'm ingesting a data about those flights, I am adding additional column flight ID, which is a combination of the year, month, day of month, unique carrier, and flight number. Basically, we are creating a column which is a really good candidate for the Bloom filter. And we are saving into our target table. So let's hit it. And then we can list the files and folders in our table folder. And what we are going to see, we are going to see additional subdirectory. So those are Parquet files with our data, snappy Parquets over here. And in this subdirectory, what we are going to see, Control Enter, we are going to get one Bloom filter for each of the Parquet file, what makes sense. And of course, it would be really nice to display the content of that file. So let me just grab one path, like I just need to extend this one. Copy one path to this filter, and let's try to see how this looks like. But unfortunately, Databricks will not let me to do that because it detects that I'm trying to mess up with some of the Delta Lake files, so I need to do a small hack. And what I'm going to do, I'm going to copy that file into my own directory over here, Ctrl Enter, and starting from now on I can query it. And that's how it looks like. So at the beginning it's not very readable and definitely doesn't looks like anything what we have seen in the theory section a couple minutes ago. But I can decode it and translate it into binary format, and voila, that's our Bloom filter for one of the files. Okay, let's now perform a search using a Bloom filter. So if we are using a Bloom filter or not, we can do by verifying explain extended in our query, and Ctrl Enter, and here we have a query execution plan including the physical plan. If you don't know how to read it, I highly recommend to watch the introduction to the Spark architecture, a link to the movie in the description. And what we can see over here is that we do a file scan Parquet with a Bloom filter over here. So it's the information that a Databricks is using, or at least trying to use, a Bloom filter which we have created. Well, in our case, we are doing a search on the column which is still in the list of 32 columns, so there is still some delta log statistics about that column. But the true beauty of the Bloom filter comes when we are setting this up on the column outside of 32 columns on which we have statistics. Which makes sense. The Bloom filter should be used for the high cardinality columns, like maybe columns with a text, and those columns anyway doesn't bring too much value to have them in the first 32 statistics in the data log. So let's remember about this one. And moving forward, what we can do is we can display the list of the Bloom filters, and this is one of the pain. It was already painful to check if we have a Z order setup, but checking on which column there is a Bloom filter setup, it's even more painful. What I have here is I have one liner written in Scala. I didn't figure out yet how to write the same in Python to get the same information, and when I scroll down I see here that on flight ID I have a Bloom filter with its standard parameters. That's it for that notebook. Liquid clustering, the most serious topic in this video. So here comes the secret, which nobody in the Databricks or the whole Delta Lake team wants you to know. Liquid clustering was inspired by this guy, who was saying, empty your mind, be formless, shapeless, like a water. You see the correlation, liquid clustering, like a water, Bruce Lee, 100% guarantee. Okay. So we will start a liquid clustering explanation on talking really about the Z order and how we can make it even greater. Well, Z order was good. We saw it, it's smart, it's really clever, but it would be great if we could have an incremental optimization, this incremental clustering. We didn't have to run the optimize each and every time. It would be great if we had the flexibility to change the column once the table is created and avoid a need of rewriting all the data all the time we are changing the column. So basically every time the user search pattern change. It would be great if we could use even smarter algorithm than a Z order, if such exists, and if we could create some visibility for the end user in the table definition. Like example, in the Z order we saw that the only really way to check which column, on which column Z order has been applied, was to go through the table history. It would be fantastic if user could check it easily by himself, for instance running describe detail, and it would be really nice if we could apply this optimization technique in a similar way like with the partitioning during the table definition. With the Z order we didn't have that possibility. And let's start by talking about the algorithm. So previously we were using, of course, a Z order. The liquid clustering is using something what is called Hilbert curve, and it looks like you can see on the left on the picture on this nice animation which I took from Wikipedia on the right. And you know, overall it's somehow similar to the Z order, but at the same time different. Looking on it you can spot the difference, but it's not so easy to spot if it's better or if it's worse and if it's really matter. So to talk about that, let's take again our table and let's do a side-by-side comparison. So the table on the left is the table with the Z order, and we already saw it before. That's how you connect the rows if you apply Z order. And the table on the right is exactly the same table, but this time with the Hilbert curve, right? And let's say that we want to split our data into 16 files, and that's what we get. And really, no matter how you look on it, no difference. So let's say that instead of having a 16 files, we would like to pack a data into 8 files, and we end up with something like this. Again, it looks the same. So let's go further. Let's say that we want to create even larger files, and let's see how those files or which rows will be selected into those files in the Z order versus a liquid clustering. So starting with the Z order, so if we want to create a bit larger file and we follow a Z curve, because that's the whole idea, those are the records, those are the rows which will go into the first file. Those records following the Z curve again, so we start from the left bottom and then we follow the red arrow, we go to the top, and those are records which goes to the second file, and then following a Z order, those are a next record which goes to the next file, and to the next one, to the next one, and to the next. So where's the problem? The problem is with the blue file. And the blue file, for those who don't distinguish colors very well, are in the column 1 between 3 and 6, and in the column B between exactly 1 and 8. And here is the problem. In one file, you have a minimum and maximum value of the second column, meaning whenever user will be doing any kind of query on that column, Spark will be forced to go through that file. There is really no way to skip it, because in the delta log we will have a statistics that the minimum value for that column in that file is 1 and maximum it's 8. So no matter what user will be looking for, 5, 7, 3, you will, or Spark will always need to read that file, and that's a problem, that we have created files which are not possible to be skipped. And now if we look on the liquid clustering and we follow a Hilbert curve, that's how first one, second file looks like, third one, fourth, fifth, and sixth. And it happens that the records which has been selected to be located in the same file are way closer to each other. We don't have this situation mix max. Well, we can talk about this red file, but even in this red file, while this is white on one column, it's very narrow on the another one. So it's still way more better compact. So while a Z order was the improvement comparing to the partitioning, a Hilbert curve, which is implemented in liquid clustering, it's simply a further improvement. And before going to the notebook, what we have here, Lake of the Holy Ghost. How cool name it is. And this is a lake where the most famous iconic scenes from the Enter the Dragon were filmed. Hong Kong. Alright, we are now in the liquid clustering notebook, and there are two things which we want to check and demonstrate over here. First of all, how can we cluster our table and later on change those clusters? And the second thing which we want to check is what's so liquid in this liquid clustering. So let's get started. The small difference between this notebook and the previous one is that here everything what we are going to see has been already calculated to make it a bit faster. So at the beginning we are creating our target table, which we already know from previous notebook with the flight data. Just this time we are using a keyword cluster by, and we are choosing two columns, years and the destination, which means that in contrast to the Z order, we can apply this optimization mechanism straight from the beginning. And then we are ingesting a data the same way as we were doing that previously, no explanation required. The first thing we want to check is describe details, and here the first interesting information will be visible for us. Once we run that command, we see that liquid clustering is a bit like a partition. It's visible on the table definition level, which is, maybe it sounds like a small thing, but if we remember a Z order or Bloom filters, checking those was a bit of pain. Here it's crystal clear. The table has been clustered, and for the clustering purpose, those two columns have been used, what is really handy. Moving forward, let's take a look on the history of the table, which is also super important. The last operation which has been performed on that table was the operation write. But if we check operation parameters, and I will scroll down a bit, we see here clustering on write status and the name of the algorithm. Meaning this is the execution of this incremental clustering. We are ingesting a data, and on the fly Delta Lake and the Databricks are clustering a data for us, which again, it's something new if we compare it with, for instance, Z-order, where each and every time we needed to run optimize and Z-order. Here, at least sometimes, because not always, as we are going to see it in the second, but at least sometimes we are going to get this incremental clustering. And now let's take a look on how our data looks like in the table folder, and I will sort it by a name. So we see that it's a standard folder with the delta log and number of snappy parquet. But what is a bit suspicious is the number of those snappy parquets. It seems to be pretty high comparing to the dataset we are operating on. And actually, if we check a size and look for the largest file over here, we are going to see that although data has been clustered, the files are suspiciously small. This is 62 megabytes. Basically, this is in bytes. If we divide it by 1 million, around 1 million, we are going to get a megabytes. So here we are having 62 megabytes, the largest file. If we remember again a Z-order, all the files there were having over 300 megabytes. So this is way smaller. And the reason for this to be so small is because it's still not final cluster, it's liquid, like a water, which we are going to see in a second. So moving forward, just to make sure that the cluster has been applied on the fly, we can run optimize, and the result of the optimize is num files added 0, num files removed. Of course it's 0 because we have seen that in this case, in this data ingestion, clustering has been done incrementally. Okay, let's see what will happen if we will insert more data. At the beginning a bit more, not too much. Here we are inserting 100 rows into our table. So very small set of the data. And by curiosity, let's check the table history to see if the incremental clustering has been done or not. So here it comes, and the last operation is, whoops, the last operation is write, and here is the operation parameters. Scrolling down, but suddenly we see the reason for skipping cannot estimate ingestion size as the query is unsupported. And I need to comment on this. I was running this query a couple of times, and I need to say that I was getting different results. Sometimes the liquid clustering, the incremental clustering was executed, and sometimes not. Even though we have this incremental clustering mechanism, running optimize periodically, it's still a good idea, and we shouldn't count too much on this incremental clustering, at least for the time being. So let's remember about this one. And now let's load way more data into the table. So here for 4 times I'm loading the same data. So basically I'm multiplying the volume of data by 5. So now we are going to get in our table 5 times more data, which is a significant change. And if we check a table history and find the last operation write performed on that table, unfortunately result is exactly the same. The incremental clustering hasn't been done, hasn't been executed. And this means nothing else than the fact that we just need to run optimize by ourselves. So let's do that. So if we look before that, if we look into the folder, we see many small files, and then we are running optimize. And after running optimize, we get information that 200 files have been removed and 8 files have been added. So definitely the optimize has changed some clusters in our table. And it's very interesting to see how the files looks in our table right now. And we just do the vacuum just to make sure that we don't look on the files which are unused. And if we look inside of our table, what we are going to see is that this time the size of the files is completely different. We are talking right now about 189 megabytes files, which are almost 3 times larger than the largest files in the previous table. And this is exactly this liquid things. Clustering will be changing and reclustering the files as long as it will not achieve what they are calling a stable size. After achieving a stable size, clustering, both incremental clustering as well as clustering triggered by optimization, will stop touching those files, will leave them alone, and moving forward will focus only on clustering a smaller files and new data. But the old data, which has been already clustered and they have achieved what they call stable size, will not be rewritten anymore. And that's the difference between liquid clustering and the z-order. If you remember, in the z-order, no matter how many times we run z-order and no matter on how big table, it will rewrite all the data. The liquid clustering does not. It rewrites the data, it reclusters them until it achieves the stable size files, clusters or cubes or whatever we call it. Then it leaves them alone and focus on the new data. Unless we delete a lot of past data, then some clusters which were stable may become again liquid, but that's another thing. And let's now see the example. So here we are actually changing the clustering columns. So alter table, cluster by month. So here we see the difference between clustering and partitioning. With partitioning, the partitions were a bit written in stone. In case of clustering, we can change those clusters. But again, we need to remember, if we had a data in the table which were already well clustered and the files or cubes or clusters, whatever we call it, has already achieved what Databricks Delta Lake is calling a stable size, it will not change those clusters. It will not rewrite those files. It will apply a new clustering for a new coming data or for the data which already exists but are in the small files, are not yet stable, are liquid. So here we are attacking problem from two angles. From one angle, we have the possibility to change the cluster in contrast to partitioning. From another hand, we don't rewrite all the data like we would do with the z-order. We leave the old data alone and we focus on the new coming data. So here we are applying this cluster by month. Previously we had year and destination. Now we have one column month. We are running optimize. And as the results of the optimize, here we have the statistics. Some files have been removed. Some files have been added. We are cleaning the storage for the sake of us to see what's the content of the file without the old legacy files over there. Displaying or listing the content of the folder. And maybe at the beginning, I will sort it by the name. At the beginning we have Delta Log as always, then we have a parquet files. We already can see that the number of parquet files went down in contrast to the previous number of the files in the table. And then we go to the right to see what has changed in the files, and now we are going to see that the size of the files is completely different than it was before. Right now the largest file we are having in the table are around 240 megabytes. Very interesting, 240 megabytes. And we have 4 files around 200 megabytes. And then we also have files, exactly the same 2 files which were present in the table before. So those files were not touched. Those files were not, we have changed the cluster, previously year, destination, now a month. We would expect that all the data will be rewritten, but not. Those files have not been touched. Those are exactly the same 2 files as, and I will go up just to remind ourselves, those are the same 2 files we were having when we were clustering the table by year and month. So again, the clustering hasn't rewritten all the data like the z-order would do. And sometimes actually it will not touch the data at all, at least the existing one. Like here is such an example. I am changing the cluster again to unique carrier and tail number, so out of the blue, but let it be. I'm running optimize, and after changing the cluster to those columns, the clustering didn't even bother to change anything. It's basically the message is, all right, he is changing that again. Let me just work on the new coming data. And that's it. That's a combination of dealing with some of the problems or the limitation of the partitioning and some of the serious pain points of the z-order, like rewriting all the data. So that's the whole thing is about. And here I'm just cleaning the data. We are cleaning the data, displaying the content of the folder, but it's not changing. And at the end, This is how we can remove a cluster if suddenly we decide out of the blue that, you know what, let's go without the clustering. So we can just alter table and the table name cluster by none. Alright, that's it for that notebook. Alright, we went through a lot of material. And the best way to continue learning Delta Lake is to experiment. Check what works and how it works. And this is especially true when it's going about the optimization. Once you expand your knowledge about the optimization approaches, you are more intelligently choosing the correct one. But at the end of the day, you still need to run some experiment and have some sort of the benchmarks to be sure that whatever you are doing is the correct thing. Now, before we will close this video, I have a small quiz for you. We have 17 questions. And for each question, we will have a couple of possible answers. So very similar to the data engineering certificate with the Databricks. The best approach is to pause the video whenever we are going to see the question and possible answers, and a couple of seconds later I will tell you which one is correct. Let's start. First question is, how to drop a schema which is not empty? Shall we drop all the table first? Or maybe drop schema, name of the schema and option all? Or drop schema and option cascade? And the correct answer is of course ski cascade. Let's move on. What is a default location for Hive table files? Frequent questions on data engineering exams. So it's worth to remember. And the correct answer is A, of course A. We were talking about it. Question number 3. Which of the following statement is creating external table? A, B, or C. And the good rule to remember is that whenever we are seeing the keyword location, this is creating external table. So the correct answer is B. What is also worth to know, and you can check it by yourself, is that you can create a whole schema as external using the same keyword location. Next question. Which of the following is correct? So, is insert into and override creating the same results? No. CCAS stands for copy into table. No, it's a create table as. CTAS always produce manage table. No, we can use a keyword location to create external one, and copy into skip files which have already been loaded. Of course, D. Next one. What will happen with table files if we run following code? Okay. So we are creating a schema. Then we are creating a table without that schema, but we are using a keyword location, so it's an external table. And then we are dropping the whole schema, and we are using option cascade. What will happen with the files, table files? Everything will be removed? No, of course, the files of the table will be untouched because the table is being registered as external. So the metastore is not authorized to do that, and you can check it by yourself. Question number 6. What is the name of the following lake? Delta Lake, Lake House, Data Lake, or Loch Ness? I will give you a bit more time, and the correct answer is yes, D, Loch Ness. Yeah, that was a tricky one because as we can see, the shape of the monster can be somehow similar to the shape of the Delta Lake. So I know that it was a tricky question, but no, the lake is called Loch Ness. Question number 7. ACID in databases stands for, also frequent question, allocation, confirmation, input, delivery, atomicity, consistency, isolation, durability, access, or accuracy. Well, for me the B is correct, and the answer is B. So it's worth to remember. Frequently people are asking about it also on the interviews, so really multiple reasons to know it. Next one. Which statement about delta log is correct? Delta log is sometimes referred as a single source of truth. Delta log keeps statistics for the first 32 columns by default. It ensures ACID compliance. It tracks changes to the data including addition, updates and deletion. Or all the above. And of course, all the above, the delta log is great, as we all know. Next one. About merge. Which statement about merge operation is correct? Merge operation is very fast with updating data, but it lacks of capability to delete the data. Well, we saw that we were deleting data with merge, so that one is probably not correct. Merge operation insert, updates or deletes rows in the target table based on the matching records in the source table. Sounds reasonable, but let's read the last one. it combines two tables by adding columns from one to another. No, it's not about the columns, it's about the rows, so the correct answer is B. Next one. So, what will happen if operations attempt to add multiple rows at the same time? And it will fail midway. We were talking about it a lot in the ACID section. And what options we have? Rows successfully added to the table will be committed and new JSON log with statistics will be created. So this is not correct, we already know. Failure is not possible as Apache Spark is fault tolerance. That's a tricky question, that's a tricky option. Operation will fail and no row will be added, or JSON log with information about error will be created. And the option C, because delta log helps us to achieve ACID, and A stands for atomicity, all or nothing. So the answer is C. 11. In which case, restoration of the table version from the past may not work. Okay, so what will happen if we run a vacuum command recently with a dry run option? Nothing. It will show us the files which would be removed by vacuum. What will happen if the delta log has been deleted? That's a bigger problem. C. Z-order optimization is being used. Is that any problem for restoring the table of the version? Not at all. And table is registered in the metastore as external unmanaged. This is also fake. The correct answer is B. Delta log has been deleted. So if we delete a delta log, we cannot do the time travel, neither query the data from the past, neither restore the table. 12. What is the default behavior of vacuum? And you can read it by yourself. Someone spent a lot of effort in figuring out those possible answers. It's not tricky to figure out the fake answers, really. And 3, 2, 1. Correct answer is, of course, D. Vacuum deletes unnecessary files older than 7 days. That's a default behavior, default time frame of vacuum. 13. Which statement about cloning is correct? Deep clone copy data and metadata without column constraints. Fake. We saw in the notebook that constraints are copied. Change made on the clone table on source will be immediately reflected in the clone, only in case of deep clone. We were running this experiment and it's not a case. If we do the deep clone, it's clone for good. The light clone, that's something what can be affected, and the light clone is called a shallow clone. And this one is vulnerable to changes in the files of the source table, like running vacuum. So the correct answer here is C. 13. Okay. So data engineering team has noticed that queries run on the delta lake table, high cardinality column. So, you know, there's such information like high cardinality or low cardinality, those are usually very important information. Takes a lot of time. So we are dealing with the optimization problem. Column is frequently used to join data with other tables. Do you remember which optimization approach do we select usually when for the columns which are being used for join? Files with table data has been already compacted and are having reasonable size, so probably there was optimize command run. What other action could data engineering team investigate? Partition the table? Well, no, because partitioning is good for the low cardinality column, if at all. Making sure that column is in the first 32 columns of the table and implement the order, or implement a Bloom filter. So we were saying that the typical optimization approach for the high cardinality column for columns which are used in join, this is frequently a Z order. Bloom filter is for extremely high cardinality, typically text columns, and it works, or it's really shine if we implement it for the columns which are outside of those 32 columns which are included in the delta log. So the correct answer is B. Next one, which statement about partitioning is correct? Partitioning table does not need delta log as naturally separate files into subfolders. So it separated files into subfolders, correct, but the delta log is still there and it's needed. It's not recommended to partition tables smaller than 1 terabytes and potential partitions less than 1 gigabyte. And with data skipping, with data log, partitioning is useless. It's not useless, sometimes it's questionable and it's not so obvious. but one of the recommendations from the Databricks is exactly point number B. So that's the correct answer. Question 16. Which one of the following statements about liquid clustering is correct? Let me read it. Liquid clustering has been inspired on famous Bruce Lee quote, "Empty your mind, be formless, shapeless like a water." Sounds good for me. The correct answer is A. And the last one. Which of the following statements about, again, liquid clustering is correct? Table can be clustered during creation, but clustering can be changed later on. Well, we saw clustering being changed. Not all the files, not all the data will be rewritten, what is actually the benefit, but you can change a clustering column. Liquid clustering is recommended by Databricks to be used instead of partitioning of and-z order. Liquid clustering should be done on minimum 4 columns, so actually by default 4 columns is the maximum on what you can do a liquid clustering, but liquid clustering we can do even on 1 column. And liquid clustering clusters files in subfolders for best compaction of files. No, there is no subfolders there. And so the correct answer is answer number B. That's the recommendation from the Databricks. Nevertheless, nothing will replace an old good experiment. So once you will play with the liquid clustering and implement it, compare the performance. Okay, that was the last one. And we are at the end. Hope that you like it and hope that it will help you achieve whatever we are trying to achieve. Make sure that you also check out the Spark architecture video because it's really good. My name is Bruce Lee, Emil Kamiński. Thanks for watching and see you soon.